Hello.
Hey, Matthew.
Hey, people. Hey, Moshe.
Hi, Matt. Matt, can I ask you, would you mind if I go first? And then you have the floor and
I think that would make sense. Yeah,
you
actually.
can destroy my entire premise.
Yeah.
Let me.
Matt, can you hear me?
Uh-huh.
You speak louder because I'm having a hearing problem. Not with the microphone, but with my ears. The dark wax or dark matter in my ears is melting.
In your ear.
Have you? Can you hear me?
Yes, I can.
Okay.
Matt, will you be able to give me full screen because I have a couple of visuals,
Yeah.
not very many.
Let
me see. Oh,
yeah. How do I do that?
I think Moshe knows how to do it.
Spotlight video.
I see you right now full screen.
Okay, so I got it.
Michael, I see you now full screen.
And I see myself full screen.
Oh, Timothy.
But that might be an accident.
I still see you full screen.
Yeah, and I do
So
too.
it probably is an accident. This is a terrible accident.
But when I need to speak, I'll need to show a couple of visuals, or else nobody will understand what I'm talking about.
Look like boss Jim Geddes filling the screen.
Yeah, I think
Boss Jim Geddes.
I think
Boss
that'll do it.
Jim Geddes.
Moshe, how do you do that? How do you give somebody else full screen?
I don't know. Right now, I see you full screen.
You gave me full screen when I made the presentation.
I think I got you covered, Michael. I put the spotlight on you and I pinned you. So I think you're good.
Yeah, I mean, if you leave it this way, I can. So can
Yeah,
you
I can
guys
see
see
Bone.
this? This is the test pattern.
Yeah, I can see David Bone.
Matt,
Who's that?
Matt,
Who's David
just-
Bohm? I
Matt-
never heard of him.
Matt, just so that you know, I can hear Michael clearly and I can hear Moshe clearly, but I can barely hear you.
Oh.
So
Okay.
either turn up your mic or.
I'll make sure to talk more.
Can you guys see this? Victor, can you see this?
I can, my God.
Yes.
It's obscene.
I know, I drew them myself. They were a big hit at the New York Quantum Meetup. Just ask Moshe.
Yeah?
I got accolades from all over.
People were throwing quarters.
Some of them were throwing rocks, but some of them, yeah, dimes, nickels and dimes.
Don't mention the rocks.
You know, Moshe, I'm going to give a very brief synopsis of the presentation I gave at your meetup.
Great.
So, and then Matt is going to completely destroy everything I've said.
Well, hey. I mean, I don't have, too many deep mathematical arguments against it. Although I'd be curious, if you can talk about like I keep noticing there's always like a paragraph whenever they're talking about Bohmian mechanics about like the particular like.
Are you kidding me?
Assumptions that go into
mathematics, or as Victor would understand it, yeah, mathematics.
Math. like for example, there's this paper I had like that's kind of cool. It's called "Understanding Bohmian Mechanics: A Dialogue," and they say stuff like, it has been proved that for almost all initial configurations, according to a suitable measure, and for all wave functions of a suitable class, the equations of motion have a global solution. Hence, with probability 1, the Bohmian trajectories never run into singularities of the velocity field, or,
Really?
putting like a volume measure on configuration space, and
oh, come on, that's
like certain things that I don't really know.
This is nonsense. This is not. I've never read anything like that, and I've never read anything that has to do with probability when we're talking about Bohm.
Well, they're like
there are people who like to pontificate about different things, and it doesn't mean.
Okay. Like another line is like, it has been shown that for the overwhelming majority of possible initial configurations of the Bohmian universe, the configurations of these subsystems look as if they were random and independently psi squared distributed. Like, I guess it's under the heading of the quantum equilibrium hypothesis.
Yeah, well, this makes sense.
Wrong.
This makes perfect sense.
If you could just, if you can talk more about that, I don't know if I fully understand.
The difference is, just to give you a heads up, the difference is Copenhagen's probabilities have to do with the measurement. That's the end result. In Bohm, the particles, of course, have an initial statistical distribution. And I make the distinction between probabilistic and statistical. Statistical means that in theory, we could measure the initial conditions of every particle. But in practice, we don't know how to do it. Just like in theory, we could measure the distribution of molecules in a gas. They all have actual positions and momenta. But we'd have to measure 10 to the 24th different measurements simultaneously. So as a practical measure, it's not. So this is a statistical characteristic as opposed to probabilistic. Got to make that distinction. But that's really beside the point, really.
Well, yeah, why don't you get started? I think we got our crew here together.
I was waiting for hundreds of people to show up.
Yes.
What do you mean? Well, who do we have? Is Andre here? David, thank you, David. David's good for showing up. We know
there's about 8 or so people.
David's I gotta say, David is my favorite participant.
I wish we could do that thing that they've been doing at the games, where we could fill a stadium with participants.
Those are fake people.
Oh, by the way, speaking of filling stadiums, I understand Donald Trump is speaking at 3:30. I don't know if he's declaring war or something else, but anyway, we should. I watch him only to see how bad things are, So anyway. So should I start?
Yeah.
So can everybody see this?
Yes.
Okay, good.
Yeah.
So let's start. So I'm going to give a presentation as a prelude to Matt's presentation, and Matt will disagree with everything I say. My presentation is it's going to be a synopsis of a presentation that I gave at the New York Quantum Meetup several weeks ago. You're all familiar with the standard interpretation of quantum mechanics, non-relativistic quantum mechanics.
Yes.
That's the most popular. It's taught in physics class, or you studied it on your own. The Copenhagen interpretation, which is a probabilistic, non-deterministic interpretation of the universe. There have been several alternative interpretations of quantum mechanics since then. And the one that I like, and many physicists like, was developed in a paper presented by David Bohm, an American physicist, in 1952, which is a completely deterministic, not probabilistic, but a completely deterministic methodology of describing quantum phenomena. Okay, so let me say up front that Bohm's interpretation and Bohm's predictions are completely compatible with Copenhagen, or what I should say, the opposite. Copenhagen is completely compatible with Bohm's deterministic predictions, and they must be compatible because we know that empirical data verifies Copenhagen as it does Bohm. So they've got to be compatible. So let's start with Isaac Newton. Isaac Newton believed that light consisted of particles, although as far as we know, he had no empirical nor theoretical evidence for this belief. Fast forward to about 1800. Thomas Young performed the very famous double slit experiment, where he shined monochromatic light through a screen in which two slits had been cut. And instead of getting what you might naively assume would be two bands of light on a back screen, he got alternating peaks and troughs of light intensity. And the only way that that Young and subsequent physicists could explain this was that the light was going through both screens and interfering with itself. The light was a wave. And after it went through the two slits, it interfered with itself to produce this so-called diffraction pattern on the back screen. We all know that. That's the classic double slit experiment. About a half a century later, Maxwell synthesized all the known electric and magnetic phenomena at the time, came up with a wave equation, and was able to show that light was not only a wave, but in fact it was an electromagnetic wave, because the speed of the wave that Maxwell calculated from his wave equation was close to what had been measured as the speed of light. And by the mid-19th century, the speed of light was, had been measured fairly accurately to within order of magnitude. Anyway, classical physics, wave physics started to break down towards the end of the 19th century, most famously with what we call the ultraviolet catastrophe, where classical physics, classical wave physics, could not predict the experimental black body radiation. It's called the ultraviolet catastrophe because the prediction of classical physics was that if you had a continuous stream of energy that in the ultraviolet range and beyond, the energy radiating from a black body would go to infinity, which is obviously unphysical, ridiculous, and not in conformance with the empirical data. So around the beginning of the 20th century, Max Planck took a different approach, and he said, well, instead of having a continuous stream of energy across frequencies, what if we quantized the energy? That energy came in packets, that light came in packets of energy rather than continuous waves. And he was able to match his theoretical prediction to the actual measured black body radiation curves. And a few years later, I believe it was in 1905, Einstein, in order to explain the photoelectric effect, showed the only way that the photoelectric effect could be explained is if light came as quantized particles of energy, which he called photons. So here we have a dichotomy. We have light sometimes exhibiting a wave-like nature, but here Planck and Einstein in particular showed that light had a particulate nature, and hence we came to the concept of the wave-particle duality. And a few years later, after Einstein, experiments were done with fermions, with electrons, that showed that electrons also exhibited a wave-particle duality, that you got comparable results with cathode rays, that is, electrons if you performed the double slit experiment with the cathode rays, you'd get this so-called diffraction pattern, just like you did with light. But we already knew that electrons were also particles. So this wave-particle duality persists to this day. Schrodinger in the 1920s, by the way, a lot of what I'm telling you already know, but I feel, brief synopsis of the history is useful.
Yeah.
Schrodinger's figured, well, if particles, bosons and fermions, can be described as waves, then they can be described with a wave equation, and hence the famous Schrodinger wave equation. Well, for a while, it was not clear what the solutions to Schrodinger's equation actually meant. It certainly did not describe trajectories of actual particles in three-dimensional space, which is what classical physics describes. But ultimately, Max Born came up with the Born rule, which said that if you take the coefficients of the solutions to Schrodinger's equation and square them and normalize them, they will give you the probabilities of measurements of quantum events. And over many, many measurements of identical experiments, of course, we know that the empirical evidence confirmed Born's probability predictions. Well, this did not sit well with a lot of physicists, most notably Albert Einstein, who famously said something to the effect that God or nature does not throw dice. Einstein believed in determinism, not probability or indeterminism. He believed in determinism until his death. And in fact, well, Einstein believed that there were what he called hidden variables, that there were external variables that were not being taken into account, that we didn't know about, which when we ultimately discovered them and reinserted them into our quantum theory, they would make deterministic predictions of measurement outcomes. Well, of course, today we know that Einstein was wrong. John Bell, in the mid-1960s, about a decade after Einstein's death, John Bell proved that Einstein's external hidden variables were not consistent with quantum theory. Well, in 1952, David Bohm came up with an alternate theory, where he started with the same Schrodinger equation that the Copenhagen people had started with, and he manipulated the mathematics in a somewhat different manner. Why did I lose Moshe? Is Moshe bored already?
I'm still here. I'm still
Oh, you're here.
Yeah, I'm just
Okay.
walking about.
I don't see you. Oh, you're walking about. That means you're bored.
I cannot
Can't tell with Victor or anybody else because I can't see anybody. Anyway, David Bohm manipulated the same Schrodinger equation. He manipulated it mathematically in a somewhat different way, and he came up with what you might call a hidden variable, but it was not an external hidden variable. It was a natural derivative, a natural derivation of the same Schrodinger equation, which had been hidden from the Copenhagen people. They never discovered it because of the mathematical methodology they used. And this new variable is called the quantum potential. This quantum potential enables you to predict actual trajectories of quantum particles and their velocities in a deterministic way, so you get an intuitive three-dimensional picture of what's going on in real three-dimensional space, which is something Copenhagen cannot do, as far as I know. Some people like indeterminism, probabilities. If you extend that to the human being, we would call that free will. People like to believe in free will, and I think this is Matthew's philosophy to some degree. Other people believe in the classical model of determinism. That's what the Bohmian people believe. That's what I believe. My belief is that nature acts according to strict, fixed rules. Nature doesn't do a mathematical calculation to decide how it's going to conduct any physical process. It knows what it's going to do, in a sense. And the only way we can describe physical processes is by a tool that we invented, that our brains invented, called mathematics, which in any case is only an approximation to what nature does. The most accurate physical theory that's ever been devised is quantum electrodynamics by Richard Feynman. I think it's accurate to something like 13 decimal places, but it's not 100% accurate. And I believe the goal of physics is to get greater and greater accuracy so that what we perceive as physical measurements conforms with our mathematical, or rather the mathematical prediction that we come up with conforms with the physical measurement that we make. Of course, our being limited by our senses, or our extended senses in the sense of measurement instruments, but primarily by our brains, which may limit us ultimately in understanding a theory of everything. Although people think we're very close, I dispute that. But let me get into some of the mathematics of. Well, before I do that, let me show you a picture of what Bohm predicted. We're all familiar with this is the double slit experiment. The double slit experiment explains a lot of the confusion surrounding quantum physics. In the Copenhagen interpretation, we say that physical particles, whether they be photons or electrons or anything else, go through both slits to create the diffraction pattern. What Bohm's theory does is that it separates the particle from the wave, so to speak. Not the wave so much, separates the particle from its potential trajectory, which gives you the same diffraction pattern on the screen over many, many particles that Copenhagen, or going back to Thomas Young's original experiment shows. And these trajectories, so an individual particle chooses one or another of these trajectories that are calculated by Bohm's quantum potential, a new quantity that he came up with that is derived strictly from Schrodinger's equation. How does the individual electron decide which trajectory to take? It has to do with the particles' initial conditions, which of course, the particles above absolute zero, they're vibrating all over the place. They have initial velocities and initial directions. And this, of course, is some statistical, probably a Gaussian distribution of these particles' initial conditions, which unfortunately we have no way of determining at present. But the initial conditions are what determines the particle's choice of one trajectory or another. The particle itself only goes through a single slot, a single slit, not both slits, as Copenhagen says. But the ultimate outcome over many, many particles is the same so-called diffraction pattern on the final screen. Now, how do we know that the individual particle takes a specific trajectory? Because you can slow down the experiment, whether you're using photons or electrons. You can slow down the experiment to see where the individual particles land on the final screen. We know they land at a particular point, and over many, many particles, they trace out the so-called diffraction pattern. I see Matthew is in agreement on that.
Yeah.
Maybe we're convincing him.
Well, I had just a minor question in a way. I look at that picture.
Yeah.
Why does often the trajectories look like they're kind of going in a straight line for a bit, and then they kind of like jump up a little bit and then continue on? It's sort of like plateauing type thing. Is that just a reflection of just there being a double slit, or like I'm just trying to understand the qualitative?
Well, there is a double slit, but I have to say that the trajectories are determined again by this quantum potential, which I'll show you how we get that.
Yeah.
And these are not all the trajectories. With greater refinement,
Right.
with greater computation. And this, by the way, is a very complicated computation. I'm sure it's done using numerical analysis on a computer. You can see that I didn't hand draw this. This is a computer derivation. With greater refinement, you're going to get many, many more trajectories. I don't see that they start out in straight lines. You're talking about the middle?
They'll often have this sort of like plateau-like shape.
Yeah.
The way it was imaged by this Aussie physicist on PBS was, it basically seems as if these jagged sort of turning points, whatever, in the trajectory are determined by the pilot wave. So you have this pattern in the pilot wave, and as the particle passes through the double slit, it is riding whatever on its own trajectory, and then it is then, in a sense, captured by the pilot wave, which then creates these turning points. That is the way, at least it was imaged. He didn't explain it in that way, but that is the way visually it was imaged on PBS.
Okay, let me address
This
that.
is a very good explanation. And the reason you see this jaggedness, it is just the peaks and troughs that you get in the diffraction pattern from the two waves. So you hit a trough, you hit a peak, it goes this way, it goes that way.
Right. And so like if the slits were like a different distance from each other, you'd get like a slightly different plateau, maybe like a longer.
Let me make a few comments. Victor is very observant in calling this the pilot wave. This is not what Bohm called it. A pilot wave is a term that comes from Louis de Broglie. At the 1927 Solvay conference, Louis de Broglie presented a theory wherein he separated the particle from the wave. He said the wave guided the particle. They were separate entities. People like Wolfgang Pauli did not like this theory and shot it down. Pauli was famous for this. was shooting down people's new theories that didn't coincide with his beliefs. So De Broglie, who was a shy and retiring kind of guy, just dropped the issue. And it was not revived until 25 years later when Bohm presented his paper. Bohm calls it the guiding wave. In any case, this is not a static wave. This wave changes over time, changes as the particles change position. They're determined by the particle positions and by the background experiment. And this is a non-local phenomenon. It's akin to entanglement. The quantum potential is a non-local phenomenon. Nevertheless, it's causal. I noticed that Matthew objected to some theories because they're not causal, but they're not causal in the sense that they're Lorentz invariant. No, they're not Lorentz invariant, but nevertheless, they're causal. They happen instantaneously, but one thing causes the other. They don't go back in time.
And also, I had a question. It doesn't matter how many dimensions you're working in. Like, in other words, I could have a one-dimensional, two-dimensional, three-dimensional Schrodinger equation. It would make no difference.
As far as I know, the physical universe has only 3 spatial dimensions, and all the other stuff is mathematical, supposition. It's a way we describe things mathematically. I don't think they're meant to be taken literally. It's like Hilbert space.
To answer your question, Matthew, the whole Bohm formalism is derived from Schrodinger's equation, Born rule, saying that the probability of an outcome is the absolute square of the amplitude, the continuity equation, and that's it. Those are the 3 inputs, and just by combining those, you get the formula that Bohm came up with for the velocity of the particle. So it was not anything new. It was just the result of combining 3 established equations of quantum mechanics. As long as those 3 equations hold in any other number of dimensions, the Bohm theory will hold there as well.
Okay.
Okay, I'm not sure I agree with what Moshe just said, but let me clarify. Let me get into some of the mathematical methodology very shortly. Like I said, Bohm starts with the same Schrodinger equation that Copenhagen does on top. It's a Hamiltonian for a wave equation. It's, on the left, the total energy equals the kinetic plus the potential energies. And the 2 formats for a solution to a Schrodinger wave equation are the 2 equations on the bottom. The first one is expressed in terms of the Hamiltonian, H. The one on the bottom is expressed in terms of the action, S. We all know what the action is, right? That's the integral of the Lagrangian over time, the integral of LDT. So pay attention to the equation on the bottom. What we do is we substitute the solution expressed in terms of the action S back into the original Schrodinger Hamiltonian, and we come up with 2 equations. One equation is the imaginary component. It's called the guidance equation or the guiding equation, and it gives the velocity of particles expressed in terms of the wave function phi. And the second equation is the real part. Does anybody know? Forget about Q for a moment. Does anybody, not Moshe, because he already knows. Does anybody know what this equation is called in classical mechanics? This is an alternative formulation of a dynamical system in classical mechanics. Anybody know what it's called? Victor,
Heat equation?
what's that?
Heat equation?
Is that David?
Yeah,
Well, but you know what it is because you were in my lecture. What is it?
I said heat equation, but I don't know if that's
No,
correct.
it's the Hamilton-Jacobi formulation for a dynamical system. You know, we have Newton's equation, we have F equals ma, we have Lagrange's equation, we have Hamilton's equation. There's also the Hamilton-Jacobi equation, which expresses a dynamical system in terms of S, the action, okay? But when we manipulate Schrodinger's equation, the real part, again, the imaginary part gives you the velocity of the particle, and the real part gives you a modified Hamilton-Jacobi. It's got, in addition to V, it's got Q, which is this expression.
Yeah,
Q expressed as a function of the wave function. And Q, let me just finish. Q is what enables you to calculate these trajectories. Now, like I said, I'm not going to do it here. Like I said, I mean, this is a computer printout. Like I said, the double slit experiment from a quantum perspective is a very complex system. It's a macroscopic system.
Michael,
Yeah.
can you put back the equations that you just said a minute ago?
For a small price, I will.
Look at the top line. The top line here gives you just the first and last. Forget about the intermediate term. It gives you the velocity. It tells you that the velocity is proportional to the imaginary part of psi star delta psi divided by psi star psi. Basically, what it tells you is the velocity is determined by the imaginary part of the gradient of the wave function. Psi here is the solution to Schrodinger's equation. That's all there is. This is the equation that gives you the trajectories that you saw before. You don't
No, I have to, Moshe, I have to correct you.
No.
The top equation gives you the velocities. The bottom equation, the quantum potential Q is what gives you the trajectories.
No, the top equation gives you the velocities, and this is the equation that determines the trajectory. Just like Newton's equation gives you an expression for the acceleration, and Newton's equation gives you the trajectories. Because what you have here, V, is the derivative of the position with respect to time. You integrate this, you get the position, you get the trajectory. So V equal to what you have all the way at the end. This is what gives you the trajectory, this and absolutely nothing else.
So what does Q give you? What does Q give you?
Q gives you just another expression for expressing something that you don't really need. All you need is that the velocity is equal to the gradient of the wave function, plus a few other terms. Factors, sorry, plus a few other factors.
I had a question. This came up in one of the papers I was reading, and they sort of gave an argument why this wasn't a problem, but I wasn't sure if I followed it. So, you know, in both of those equations, you have this like denominator. In like the top one, it was like psi star psi, and then the bottom one, it was just psi. So what happens if they go to 0?
And it's probably a classical experiment. I have to tell you, I don't agree with Moshe, but I'm going to have to research this.
Like if you know,
the velocity is,
I can answer your question. I can
Well,
answer your question, Matthew.
okay, yeah.
Psi star psi equals to 0 means that the particle is not there. Psi star psi is the probability of finding the particle at a given point. If the particle is not there, there's no sense of talking about the velocity of the particle at this point.
Nice.
This is an expression that gives you the velocity of a particle at some point where the particle is, or at least has some probability of being there. If it has 0 probability of being there, then don't talk about its velocity.
Okay.
But this is an excellent question, Matthew.
Okay, what I need to add is that the quantum potential and the velocity are non-local phenomena. They're akin to entanglement, for example. They are causal, but they do not respect the Lorentz transformation.
Can you put the equation again? Put the same equation again. Now, the top line gives you the velocity as the gradient of the imaginary part of psi star, gradient of psi, and so on. This expression that you see there is dependent on whatever else goes on in the universe. If in the universe you have, if it's empty, you have one expression for this. If it is full of stuff, you have another expression. If you have a potential, whatever. So what you have on the right-hand side depends on the rest of the universe and the configuration of the rest of the universe. And where you have the non-locality is that according to Bohm, when you change the rest of the universe, the impact on this expression is instantaneous. If you look at the impact of a particle light years away, it moves, it doesn't move, whatever it does, you don't have to wait for the information to get to you at the speed of light. The information is instantaneous.
Okay, I'm gonna.
This is where you get non-locality in the Bohm configuration, and this is going to correspond to the non-locality in wave function collapse in Copenhagen.
Okay, let me express my disagreement with Moshe. Actually, I agree with them. The wave function depends on everything that's going on in the universe, but as a practical matter, we could separate a subsystem from the rest of the universe. The rest of the universe has a very small effect, like in the double slit experiment. The rest of the universe doesn't have an effect on it to speak of. What's important?
Let me be more specific about what I mean by the rest of the universe. When you have two particles in the singlet state, when you measure the spin of one particle, it has an immediate effect on what happens at the other particle. You don't have to wait for this information to propagate at the speed of light. You measure the spin of one partner in the singlet. This caused a change in the configuration of the universe, and this change of configuration has an immediate effect. Even if the partner is light years away, it doesn't have to be nearby, it can be light years away, the effect is going to be instantaneous. And
Okay.
this is where the Bohm non-locality meshes in with the Copenhagen non-locality of the wave function collapse.
Okay, I'm going to have to, we're talking apples and oranges here. Spin is a relativistic phenomenon. Spin is something that's inserted by hand into a non-relativistic theory, whether it's Copenhagen or Bohm. Where'd you go, Matthew? This is important.
I'm listening. I'll be right back.
Spin is a non-relativistic phenomenon that is predicted, ironically, by a relativistic quantum field theory. Dirac's equation predicts spin naturally. No non-relativistic theory predicts spin. Bohm doesn't predict spin, nor does Copenhagen. It's inserted by hand.
So what? It's inserted by hand. So what? It works
It has nothing
beautifully.
to do with whether you agree
insert
with
it
Bohm or
by hand.
Copenhagen.
You insert it, it does. You insert it by hand into Schrodinger's equation, and you get the precise spectrum for the hydrogen atom. You solve the Schrodinger equation for the hydrogen atom with spin for the electrons, and you get the correct answer.
Okay, but the fact of the matter is that it's inserted by hand, not a non-relativistic theory, either Copenhagen or Bohm, does not predict spin.
So what's your point?
Whereas, well, let me finish. Whereas a relativistic quantum field theory actually does predict spin. Dirac's equation naturally predicts spin half
So what's your
for
point?
fermions.
So what's your point?
The point is that the question here is, do you believe in Bohm, which is deterministic, or Copenhagen, which is probabilistic? Spin is a whole separate issue. But what I will say is that the quantum potential is somewhat like spin in that it is a non-local phenomenon. It violates Lorentz invariance, but it's causal.
No,
It's causal.
it violates in and of itself. It does not violate anything. Where it
Sure it
becomes
does. It's non-local.
let me finish. It becomes non-local only is as far as you have to look at the impact that the rest of the universe has on this potential, and this impact is instantaneous. If you said you have this potential, and if I change things in the configuration of the universe, well, I will have to wait for the speed of light for this information to propagate before it changes this potential. Then it doesn't. Then it looks like a regular kind of quantity.
I agree with you, Moshe.
Where it becomes non-local is the statement that the impact of any changes to the configuration of the universe are being felt instantaneously by this kind of potential. That's it, end of story.
And that is the definition of a non-local phenomenon, whether it's spin,
This has nothing to do with
entanglement, or this quantum potential. There are certain physical phenomena that are non-local. They are not Lorentz invariant, as Einstein wanted everything to be. Nevertheless, they are causal. So it's just that they happen instantaneously. Now, Matthew had this very objection in his notes to the presentation he's going to give, that he doesn't accept Bohm in part because it doesn't predict spin, but neither does Copenhagen. Spin is a relativistic phenomenon that is predicted by a quantum field theory, like the Dirac's equation naturally predicts spin. Neither Copenhagen nor Bohm predicts spin.
That's one way of looking at it. Another way of looking at it, an historical way of looking at it, is that spin is an experimental discovery. Spin was discovered experimentally, and this is without any relativistic formulation, nothing to do with relativity.
But it does, because it's predicted by Dirac's equation, which is a relativistic.
No need to repeat it. We all know this. We all know this.
Well, that's why it's relativistic.
Yes, but it can be incorporated, and it has been incorporated very smoothly into the Schrodinger equation.
Of course, but it's inserted by hand. It's not a natural consequence.
It is inserted by hand as an experimental fact. Isospin has not been predicted by any relativistic theory. Isospin has been inserted by hand by Yukawa and Gell-Mann, but it has been inserted by hand. It has not been predicted.
Well, isospin is a mathematical concept. Isospin is not something you can measure. It's not a real physical concept. It's a mathematical concept.
It can be measured.
No, it's a real, not isospin.
Isospin is measured, of course.
Only in terms of other measurable quantities.
I don't know what you mean in terms of others. It has been measured. It is a conserved quantity. It is a conserved physical quantity.
Well, this is where I make the distinction between a mathematical property and a physical property. There's no such thing as an isospin meter where you can stick it in and measure isospin. You can't do an experiment that measures isospin like you
Of
can,
course you can.
like you can do a Stern-Gerlach that measures spin. Spin is a real physical property. Isospin is a mathematical construction.
No, isospin is a conserved physical property. You cannot violate conservation of isospin.
Okay, respectfully, I disagree. It's a conserved mathematical property derived from other conserved, derived from things like charge. Isospin, the concept of isospin came up with the fact that the neutron and the proton have the same mass, but they have different charges. So we can mathematically describe them like we describe spin.
Yeah.
But that's a mathematical description. That's not a real physical description. Whereas spin is actually measurable. It's measurable with the Stern-Gerlach.
I had a question.
So this is a philosophical difference.
Yeah. I had a question, not about isospin, but just, has anyone ever, like, tried to extend Bohmian mechanics so that the changes in the quantum potential did propagate, like, at the speed of light? And
no,
like,
it doesn't.
sure,
It's like saying, can entanglement propagate at the speed of light? The answer is no.
right.
But you're talking about people have tried to extend Bohmian mechanics to a quantum field theory, to a relative. Again, all quantum mechanics, Bohmian and Copenhagen, are non-relativistic. They cannot describe spin. They cannot describe particle creation. For that, you need a quantum field theory, which does do that very well. Whether it's Dirac or Klein-Gordon or Proca, which is the spin 1 equation. But people have attempted to extend Bohm to a relativistic theory.
Yeah, I mean, I just mean,
And people claim that they have succeeded, number one.
They have?
Coming up with a relativistic version of Bohmian mechanics, and also have particle creation and annihilation.
Really?
In the context of,
Which paper is this? Which paper? I want to read this.
I don't have it offhand. I have to look it up.
It's not Doran Goldstein. Is it Goldstein?
No, it is
because
not.
Their papers are complete garbage.
That's not the paper I'm talking about. I don't have it in front of me right now. I did mention it a few weeks ago.
Email it to us, because I'm not aware of this, and I don't think Andre is aware of it either. So if you could email it to us.
You should be, because I mentioned it. I did mention, for instance, this kind of approach to particle emission and absorption. I did mention this kind of approach.
What I've read on extending Bohm to Goldstein, and Moshe may have more advanced information than I do. What I've read are papers mostly by Durr, D-U-R-R, well, I guess it's German, and Goldstein. And what they do is they freeze, they take foliations of space-time. They freeze time and try to connect the foliations some way. And what I've read, it has not been successful. But why should it be when we have a perfectly useful quantum field theory? Again, non-relativistic theories, you can't make them relativistic. You got to come up with a different theory. And despite what people believe that QFT is an extension of quantum mechanics, that isn't so. It's a completely different theory where you're quantizing the fields, and the fields are creating particles through field excitation. You have particle creation and annihilation, which you can't explain with any kind of non-relativistic quantum mechanics. So why even attempt, unless Moshe, has more information on this, why even attempt to expand any non-relativistic quantum theory, which again is only an approximation to things that it can't possibly explain because these phenomena are relativistic, namely spin, particle creation and annihilation. These are relativistic phenomena that you need a QFT to explain, and which QFT, the established QFTs explain very well.
Have people tried to explain the Bohmian non-locality in terms of wormholes?
I'm not even interested in wormholes. To me, that's science fiction. But the thing is, why even bring that up? I don't know.
Well, I just mean you have like a non-local effect, so maybe it's because part of the pilot wave is like leaking through a little wormhole.
Yeah, but Matthew,
Why
is this not science fiction?
What I do know is that Susskind and Maldacena are using wormholes to explain non-locality in Copenhagen mechanics or in quantum field theory.
Yeah, I read some of their papers about that. Yeah, that's sort of what I was thinking.
Look, my philosophy of science is
The basic philosophy of Michael is the basic philosophy of Michael is, can I just say one thing?
Yeah.
Is that something is rotten in Copenhagen.
Okay. Tickle me because
Yes,
I forgot to
Hamlet.
laugh. My philosophy of science is that science is an attempt to explain empirical data. Wormholes, in my view, are science fiction. There's no empirical evidence. I could make up all kinds of fake universes that are completely mathematically consistent. Again, math is not science, and certainly science fiction is not science. Wormholes are garbage.
Evidence for gravitational waves. For 50 years, there was no empirical evidence for some massless scalar that gives mass to all other particles. So the lack of physical evidence does not mean automatically that this thing does not exist.
No, and I've answered this before. The pursuit of various theories that have not been proven yet is very worthwhile. I agree with you. But until there's empirical evidence, it's not science. Now, let me tell you something about, what was the first thing you brought up? About gravitational waves. Gravitational waves are completely explained by Einstein's relativity, a classical theory. They are a nonlinear effect of Einstein's general relativity. The Higgs boson, I've been reading a lot on that. The Higgs boson may have been explained by statistically invalid information. And by the way, there are 4 possible channels for discovering the Higgs boson. 2 of them sort of confirm the Higgs boson, but we're left, and 2 of them are in complete opposition to the existence of the Higgs boson. But the 2 channels that do confirm the Higgs boson confirm 3 statistical blips. So is there 1 Higgs boson, or are there 3 Higgs bosons? Or are there more Higgs bosons? The classic statistical methodology for confirming a particle statistically is 5 sigma. And the Higgs boson, depending on how you look at it, have only been confirmed up to about 3 sigma. And if you do a real statistical analysis—
Last time you said 1.8.
1.8, yeah. If you do a real statistical analysis, the Higgs boson may have only been confirmed 50-50. But like I said, this is all political.
The confirmation of the Higgs boson is a confirmation of a decay process.
That's what I said. There are 4 decay channels.
Where the sum of the masses of the particles into which the Higgs decayed are then summed, so as to create the unobserved Higgs boson. That is how.
Victor, you're about 5% correct and 95% wrong. It's not just the masses that they decay into. The spins have to confirm, and whether or not the particles came from a scalar or a pseudoscalar particle. And this is not, as far as I know, this has not been confirmed. And by the way, like I said, there are 4 known decay channels, 2 of which are used because they sort of statistically confirm the Higgs. The other 2, instead of having a statistical blip at 125 gig, they actually have a blip going in the wrong direction. They're denying the Higgs existence.
Okay, forget about
What
it.
does this
I
have to
never
do with the
mentioned
price of
Higgs.
Bohmian apples?
What's that?
What does this have to do with the price of Bohmian apples?
I'll tell you what it has to do, because the way we discover particles nowadays, you know, in the old days they used the cloud chamber. You could actually see the track of a particle. But today the lifetimes of the particles are so small you can't use a cloud chamber. So you can't see the trajectory. The only way to do it is over gazillions of measurements using statistics. And we all know statistics can be fudged any way you like to prove whatever you want to prove or disprove. And the statistics basically suck. They were so anxious to get this proven. Why?
What's the point?
The point is that it has to do with funding, because they couldn't come up with supersymmetric particles. Oh, they were going to discover supersymmetric particles right off the bat.
Okay, I don't accept
As soon as you
this
get into
argument.
politics
I do not
or the
accept this
politics,
argument at all.
They were
As
under
soon as you get
political and financial pressure to come up with
Okay,
confirmation.
Okay,
fine.
Michael,
This
Yeah.
is
as soon as you
this
get
is your
into
opinion.
politics or the politics of science, you become a little bit, this is a friendly criticism.
This is not
become
my
a
this is
little
not
bit-
my theory.
You become a little bit of a bull in a china shop. And then
No,
that
it's-
bull
listen,
in a
but,
china
Victor,
shop
I know what you're going to say, Victor, and I resent it. The
Okay,
fact of the
becomes
matter,
a herd, then
One
becomes a
moment.
herd of
Let-
bulls in a
let-
china
let me
shop.
make a
And
proposal.
finally, the running
One
of the
moment,
bulls of
guys,
Pamplona.
time
So
out.
just
Okay, I'm gonna-
watch
Let
when
me
you get into
propose-
the
Let me
politics of
propose that
science.
right now we stop talking politics and we start talking physics.
okay,
No more
let's start
politics,
talking
only
talking
physics and
physics.
nothing but physics.
I'm going to refer you to a very prominent scientist he was a professor emeritus at the University of Toronto, and he's at the Perimeter Institute. His name is John Moffat, Moffat, and he is the one who and a bunch of people who agree with him that where I got this information. You know, this is not something I'm making up. I'm not smart enough to make this up. But John Moffat, who was a very well-respected physicist, says that the statistics that were used to confirm the Higgs particle suck.
Okay. We're not talking about the Higgs boson today. No more discussion of the Higgs boson. Let's
All right, so
continue.
where were we?
There's David Bohm.
Yeah, so what's your
So
concluded?
like, where's Waldo? Where's David Bohm?
All right, the reason you never learned about him, again, I repeat, is because he was accused of a communist affiliations during the
You told
McCarthy
us, yes.
era, and he lost his job at Princeton because of these accusations. He went into self-exile, and he was untouchable in the American physics community. I will state that Einstein also taught at the Advanced Institute in the early 1950s, and Einstein was still alive at the time that Bohm published his paper. I don't know, but I wonder if Einstein and Bohm had any kind of relationship, and if they did, what Einstein thought of Bohm's theory. I haven't been able to find any evidence of that. What about you, Moshe? Did Einstein know about Bohm's theory?
No doubt in my mind that Einstein knew about Bohm's theory.
He did. So what did he think of it?
I have no idea, but there's no way he could not have known about it. The thing
Yes.
about Bohm's theory, as far as I understand, the reason we don't hear more often about it, number one, it does not make any single prediction different from classical quantum mechanics. So many people figured, well, we already have a theory that makes exactly those predictions. Let's continue using it. There's no need for another one to pop up. We already have books, you have everything, let's continue to use it. Number two, at the time, people did not think there would ever be a way of coming up with a relativistic version of Bohmian mechanics. So they figured, well, we have classical mechanics, we can come up with a relativistic version. We have a relativistic version of quantum mechanics. With Bohmian mechanics, we
Wait. Do you believe that QFT is a relativistic version of Copenhagen? QFT is a completely different theory. It involves second quantization as opposed to
quantum
first.
electrodynamics, quantum
That's not an
electrodynamics.
extension of quantum mechanics. That's a completely new theory.
No,
That discussion for maybe next meeting, where I was going to discuss second quantization. We can have it out there. Yeah, I think that's an,
Yeah,
you know,
where
that,
you have field excitations that create particles. What does that have to do with non-relativistic?
I'm talking about quantum electrodynamics.
Has nothing to do with Copenhagen.
Quantum electrodynamics comes from two sources. Source number one, special relativity. E square is equal to m square plus p square. Source number two, that P and E are operators. You put the two of them together and you get the Klein-Gordon equation.
The operators in quantum physics are field operators. The operators in quantum field theory.
No, I'm not talking about quantum field theory.
What are you
I'm not
talking about,
QED. I'm not talking about quantum field theory. I'm talking just about quantum mechanics and quantum electrodynamics.
QED is a field theory, isn't it?
Where does the Klein-Gordon equation come from? It comes from special relativity, E square equal m square plus p square, and it comes from Copenhagen quantum mechanics, where E and P are operators. That's it. You put those two ingredients together.
But the operator, Moshe, with all respect, the operators in quantum field theory and QED, which is a quantum field theory, the operators are the fields. They are not position. Position is demoted to a parameter. Position is not an operator. And momentum is the momentum of the field. They are field operators. They are second quantizations. They are not first quantizations. Am I correct, Matthew, or am I wrong?
No, you're not wrong. I see that there's this sort of debate about what quantum field theory is. And I think it was like Steven Weinberg in his book, like takes a particular kind of position. You know, does quantum field theory arise as simply the second quantization of quantum mechanics, where for each basis state in the ordinary quantum theory, you introduce a quantum harmonic oscillator that just keeps track of the number of particles in that state. And that makes the continuity with, normal quantum mechanics sort of apparent. Another way of expressing that continuity is to say, no, actually, quantum field theory isn't second quantization at all. It's just first quantization of a field. And that's the position that Weinberg takes.
Okay, you're talking semantics.
Which is that when you introduce interactions into quantum field theory, it becomes impossible to simply relate the theory back to some original second quantization.
Okay. Quantum field theory predicts.
That's the whole debate. I think we should sort of table this and save that.
Okay, let's table it.
It's a very.
I've got an important meeting in the next room. I'll be back.
Wait, where'd you go? Has anybody, here's a random question that I was thinking about related to this stuff. Has anyone been following Stephen Wolfram and his crew? They've been the last couple months coming up with their own theory of everything and publishing results. And I found some of the things they were talking about kind of relevant to the larger discussion about determinism. Wolfram, famously was a physicist and businessman, gave us Mathematica, etc. And recently he's gathered a bunch of young people together and they're trying to extend his sort of neo-computational theory of fundamental physics. And one of the things that I find interesting about it.
One moment, Matthew, can you make sure that we see you on the screen?
Yeah. Let me unpin. Oh, there we go. Okay.
I still don't see you on the screen.
Neither do I.
I see Michael's.
Oh, there it
now I
There he
see
is. There he is.
Here, yeah.
The Amish have arrived.
So yeah.
Finally.
You need that hat.
So two things to say about Wolfram's stuff, which I find interesting. You know, I don't think they've explained everything that they want to explain yet, but there's a lot of really cool ideas. And like two of them I'll mention because I feel like they're a little bit relevant. One is that they're interested in computational rules, but
Computational what?
computational rules,
Yeah.
but of a non-deterministic sort. And what I mean by that is, like, for example, say like a string substitution rule where you're like, oh, here's a string and we're allowed to, you know, turn A into AB or C into D or something like that. Or
Is it specifically a variant on string theory?
No.
it's
No, it's like pseudo-random numbers.
sure. It's like a lot of, so they also use like graph rewriting rules. And what's interesting about it is indeterminism or non-determinism enters into their theory because there are often multiple ways to rewrite the same string. In other words, they have a system of rules, but at any given moment, it's like ambiguous. There's not like one way to apply the rules. In other words, you could do this rewrite or you could do that rewrite. Just like in normal, you know, logic, you know, you could, given some string of symbols, well, you can apply this axiom or that axiom. There's not necessarily only one. And then they try to derive a kind of discrete version of quantum mechanics by saying, the universe has a definite rule, but is one of these non-deterministic rules, and actually all possible string rewritings are done in parallel.
And instead of just the rewriting of the string, there's also the recursive process, which is now occurring on screen. So we have two Matt Weisses on screen. I just wanted to point that out, yes.
Interesting. Oh, so that's the difference between pinning and spotlighting. So if oh, no, never mind. Wait, can you still see me?
I can see you.
Oh, okay.
Oh.
Now we see Moshe. Now we see me.
Gotcha. All right. So I find that interesting. Like they'll sort of have it that all possible string rewriting rules are applied, and they'll sort of play out all the things in parallel. And then they're interested in the cases where the rules lead to the same result, even though you can take different paths to get there. And then they use this sort of like theorem that says that, like, given any set of rules, you can always complete them in a way such that if there was a situation where there were multiple rules to apply, that they will always kind of collapse back down to giving you the same result, no matter which sort of path of rewriting you took. And they're sort of saying like, that's what happens in quantum measurement. You kind of like adjoin some rules that make that give the system the property that they call causal invariance. In other words, there may be ambiguity about which rule to apply, but in the end, it doesn't make a difference. But then one of the other interesting things that they do is they say, well, hey, so that's a situation where you have a definite, albeit non-deterministic rule, and there's ambiguity about how to apply it.
Can I ask a question?
Yes.
Why am I the star? And I see Marty was the star before I was.
I
But anyway.
talked.
Oh, you talked.
I see.
Every time you talk, you become a star.
You know, I know you're a musician, Marty. I didn't know you also talked. Can you sing?
Actually, of
But-
course.
But I have a question. You seem to be confusing math with science. You're talking about rules that were made up by men or women to try to describe physical processes.
Yeah. So Wolfram.
And they're indeterministic only because we don't, know which rule is going to work. But do you think that nature doesn't know what it's going to do beforehand?
Well, I'll say two things. I mean, in some ways, yes, I do think that, but also B, Wolfram and his crew are quite explicit that what they're doing is trying to chart out the space of all possible rules. So they don't pretend that any particular rule that they choose has anything to do with the physical world. They're interested in mapping out the space of possible rules. And that's that's sort of like a lot of the work that goes on in string
The
theory.
many rules theory.
Where you're trying to explore the space of not just any theory, but the space of possible theories itself. But the other thing I'll say about the Wolfram stuff is that they go like one step higher. I just was reading this last night. And, and say something like, well, we could fix a rule, albeit non-deterministic, and have it, there's this ambiguity about how we apply it. We follow each thing out in parallel. But like, why not imagine that you could have like any possible rule, and then given a particular state, every possible rule is applied in parallel. And for each rule, each possible update is done in parallel. And so you have this sort of like meta space. And for them, they see, their sort of philosophy is that it's not just that there's ever going to be one rule in physics, but that nature evaluates in parallel all possible rules, all possible laws in parallel. And the question is more like, when does it not make a difference in a way, which rule you happen to describe your system in?
Matt, this sounds like Epworth's multiverse.
Matt, I think there's an element of a very strong underlying element deriving from scenes in your childhood, and I'm not talking about mama and papa. I'm talking about your this ongoing counterpoint on free will and determinism with your friend. I think there's an ongoing underlying subjectivism in the way in which you're applying the issues, the more Kantian metaphysical issues about free will to physics and the way in which you're relating them. And I think you are somewhat trapped in a form of logic that ends up in an illogic. And I think there is a Kantian solution to it. I mentioned it before, but I don't think I made the point, or that you perhaps understood it. There is absolutely no necessity that even if you assume that the universe is super deterministic, and that therefore each thought, each word, each movement of consciousness is, in this intricate and irreducible way, predetermined, that you cannot simply make use of Kant's idea that we should act as if we were free. My version of that is we can act as if we were free. So it's even more open-ended. It doesn't have the imperative in it. So in other words, you don't have to be trapped into assuming what is essentially an anti-science view, the anti-causal view, because of the avant-gardism of Niels Bohr and his cohort. You do not have to do that. I mean, it was Bohr, someone especially who dismissed de Broglie in 1927 and sort of humiliated him with his insistence. But
it was
I'm not accepting either, Copenhagen or many worlds or de Broglie-Bohm or objective collapse or any of the schools. I'm not accepting any of them. So, but I think, and I think you can, and this is what I would argue. I think there's something about Bohm that feels too neat and too streamlined, even if it finds a derivative in the Schrodinger equation and therefore doesn't have the elegance of simplicity of Schrodinger. finger.
Simplicity is the rise.
I think
Victor,
that you
you
can.
weren't paying
Let me just
attention.
finish this thought. You spoke for. So that I think what you can do is reflect on the possibility that first of all, not the possibility, the certainty that we do not know the nature of the quantum realm, and that it can be anywhere along the spectrum from particle with wave-like properties, wave packet, or wave packet with particle-like qualities, or an oscillation in the quantum field, or a probability cloud. It can be anywhere in there, and no matter what the actual condition happens to be, it's nonetheless determined. It's determined, but we may never be able to determine it. And so even if you're in what seems to you to be this confining, closed universe, there is no divine being that is doing this. It is nature that is doing it. And even if every thought of yours is already channeled, and because you cannot make a decision about how each neuron is going to fire and how the neurons are going to array.
Victor, excuse me, emergency, your house is on fire.
Yeah,
Your house is on fire, vacate. I have no idea what Victor
So
just
that's
said.
the move. The move is a very simple Kantian one. You say to yourself, I can act as if I were free, no matter how unfree I am. And since I'm not a divine being, and I'm not omniscient, and I'm not outside the realm of physics, I'm unfree. But nonetheless, I can act as if I were free. And therefore, you don't have to be trapped into this avant-gardism. I happen to be utterly fascinated by all the avant-gardes in every single realm of the arts. But, I'm a super determinist.
Yeah, Victor, I was thinking about your position. Yeah, and I recognize that it's not the Bowman position. And I think, for example, even at the level of, okay, you assume a deterministic picture of the world, or even if you don't, even if you say that like our brains or our bodies are somehow determined, that doesn't mean that anyone could in practice predict it. Not only because, it would take a really powerful computer or whatever to, do the calculations, but, or another way to put it is like something like, if you're, trying to use one little part of your brain to like predict your own behavior, like there's no way it's going to be able to outpace the whole rest of your brain and figuring out what you're going to do. Like, in other words, even in a deterministic universe, no one can predict your behavior, generally speaking, faster than you just acting, not even yourself. So yeah, I'm perfectly aware that in a deterministic world, there are like going to be hard limits on, how you can actually make use of that determinism. It doesn't necessarily mean that you can predict your own behavior. It doesn't mean that you can predict the behaviors of others around you. It doesn't even mean that you can predict the results of physics, because as we well know, the world's very complicated, lots of tiny things happening, which we are forever ignorant of. So yeah, I mean, I understand that determinism is
compatible
with subjective. Yeah, like
you got me. Okay.
But then it seems to me that, to flip the argument around, that determinism is a completely unnecessary hypothesis. I mean, what difference in a way, if it makes no difference in a way, then, why hold on to determinism, particularly as, and, I know Moshe was like, no politics. I feel like the stories that we tell, our children or whatever, make a difference in how they approach the world. And so, if we're telling them that, nature is this way and there's nothing you can do about it, I don't see what value that has. Like what mileage do you get out of it? Because it doesn't lead to any new predictions. It seems a completely unnecessary, tangential sort of hypothesis.
Yeah, but Matthew, can I comment? You know, and this has been a reason given for why Bohm's theory has not caught on. My belief it was because he was accused of being a communist and he was an untouchable after that. But the reason given by many people is that it doesn't produce any new physics, that it is completely consistent with Copenhagen. Nevertheless, it provides an intuitively explainable description of what's going on in real three-dimensional space, which Copenhagen doesn't. And isn't that what science, what we use science to try to help us explain what we see going on in real space?
No, I mean, 3D space is a construction. I
Oh,
mean,
no. 3D space is real. Anything higher than 3D space is a construction.
for birds who fly around, you know, perceive the space that they live in differently than we who are generally confined to the surface of the earth. Like, I don't confuse the way that I represent the world for the way that it is.
No. We're limited by our senses and by our brains, yes. But we have no empirical evidence that there is anything other than three-dimensional physical space. And all these
Let me put it this way.
let me just finish. And all these
Okay.
invented spaces are mathematical constructions. They are not, you're confusing math with physics. And let me just comment on what you were talking about before, about the many possibilities of describing something. This sounds to me like Everett's many worlds, which is irrelevant in the sense that there's no empirical evidence for it, nor can there ever be, apparently. So what is the point? We use math and science to describe what we see as best as we can, not to
One moment.
invent universes.
Let me propose some ground rules for how we talk in this forum.
Yeah.
We are speaking in English. If we want, we can agree that everything said here will be said both in English and in French. It will be the same thing. There will be no advantage whatsoever of saying it in both English and French, but it will take more time. Similarly, we can say everything we say here using the language of Copenhagen, and in addition to this, using the language of Bohm. Since the two do not have any distinguishable predictions, they're equivalent. I don't see any advantage of saying it both in Copenhagen and Bohm. And since everyone is familiar with Copenhagen, since most of us grew up with Copenhagen, I propose that we just stick to the Copenhagen language.
Moshe, they are not equivalent. They are consistent. They are not equivalent. There's a difference.
Empirically,
Bohm,
they're equivalent. They make the same predictions. That's what I mean by equivalent.
But Bohm describes it better. That's why it's a better theory.
Good.
It describes it in a way that is intuitively understandable to us.
Macron says that French describes things much better than English.
If you're French, it does, because it's more intuitively appealing.
Okay.
There's in Copenhagen, it strikes me that you have the same metaphysical property that you find in many worlds, or in what I'm calling, his name is Wolfram, many rules. I think what you've got is open-ended possibilities for trajectories, right? In Copenhagen. And this is, it's a desire for open-endedness. It's a description that is prismatic and that is fascinating for moderns, but I see no basis other than essentially the application of metaphysics to physics for using that kind of description, no matter how intricate the underlying processes, no matter how many hidden variables, hidden parameters, hidden conditions there are at the nano level all the way to the cosmological level, it can be a deterministic and need not be a set of open-ended possibilities. We can't foresee it, and it's highly unlikely that we will ever foresee it. I'm not Laplace's demon. I'm not a vast intellect, and I'm not a divine being. But nonetheless, there is that which is in Copenhagen in the sense of the possible trajectories, which it's the same metaphysical idea in many worlds and many rules.
So, I mean, my thing is that, you know, I feel like the conceptual language that you're using is, you know, the world's this way and we might not know how it really is. And so we have an effective freedom, even though we are determined by things outside us. And, you know, I'm much more interested in, say, you know, what John Wheeler would call the participatory universe. In other words, one which looks at all things as participants in the shared experience of reality. And it seems to me that, you know, if you were going to educate a populace to be, you know, democratically activated, to view themselves as agents who have the power to change the rules. I mean, to me, it seems that all of this stuff has political implications in the sense that, you know, the question is, you know, when we use the word law, right, there's two meanings, right, which are overlaid. You know, one is physical law and the other one is legal law. And, you know, which is the metaphor for which? I mean, it seems to me that, you know, the standard way of thinking about it is like, well, you know, physical law is immutable, but, you know, human law is changeable. But it seems to me it's not inconsistent to reverse that equation and to say that physical law is just as mutable as legal law, that in fact they are the same concept, and that, you know, in the end, you know.
You're almost saying that the ideas in physics are going to somehow predetermine the zeitgeist. I mean, this is simply untrue. So take the example, say, of Laplace. I keep mentioning it. Take the example of Laplace's vast intellect. He is at the intersection between probabilistics and superdeterminism. His vast intellect is superdeterministic, yet he was refining Bayesian probabilities at the very same time. So, and when is the time that it's the late 18th century, right? The second half of the 18th century and the early 19th century. And this is the age of what? It's the age of the Enlightenment. This is the time when everyone is reading Diderot's encyclopedia, when they're reading Montesquieu, when they're reading Rousseau, okay? When the French Revolution occurs, which is, unlike ours, a genuine revolution, political and social.
What's
okay?
the point?
It was also a time.
So what I'm saying is that the ideas in physics do not somehow perfectly align with the zeitgeist in a political sense, and therefore predetermine the outcomes. It's as if you're frightened that if a child learns that the cosmos is somehow causal, that they will be unable to act as if they were free.
Can I say something?
I'm not going to say that it's totally deterministic, right? I mean, if you go in the 19th century, like this is the point counterpoint, Hegel versus Marx, right? Hegel wants to see the material reality in which we live is somehow conditioned by philosophical ideas, and Marx tries to turn it on his head and say our philosophical ideas are, you know, just superstructure on top.
Can I ask a question, Matthew? Do you believe in causality?
Yeah, but
okay. Well, what you do is based on your moral code, and your moral code comes from all your past experiences, for good or ill. And so does your so-called free will. What you decide you're going to do is based on what came before, your experiences before. So if you believe in causality, I don't know how you can believe in a non-deterministic universe. Hegel, all these 18th century philosophers were not physicists.
Quantum mechanics is perfectly causal, but it's indeterministic. I see that.
Okay. Well, see, this is the problem, that the Copenhagen view of physics has given people, the Copenhagen view has given people who believe in free will the license
Exactly.
to
That's
perpetuate
exactly my
this.
point.
But Copenhagen is wrong as far as a lot
Okay,
of us.
let Matt speak. Let Matt speak.
For multiple centuries, people who didn't believe in determinism were systematically excluded from the scientific community. They were regarded as either backwards, superstitious, primitive people. Enlightenment was like coincident with the belief that white rationality had discovered a single and like unique method which allowed you to discover nature. And like as such, huge amounts of the diversity of human experience were shut out completely. And so, yes, that is exactly what I find exciting about quantum mechanics. No longer can someone say believing in free will is non-scientific. You can't make that statement.
And you can't say the opposite.
Yeah.
The thing is, you're imposing, like I said last time, you're imposing your value system on the universe. The universe doesn't care about your value system.
That's my point.
And 18th century philosophers were not physicists and didn't understand as well as we do now how the universe works. So all of their philosophy, for good or ill, is based on assumptions which may or may not have been correct. Now, yeah, you have a certain moral view of the way things should be. Again, you can't impose it on the universe. The universe is not moral or philosophical. Universe reacts according to fixed rules. And by the way, you're part of the universe, so you react the same way, whether or not you realize it.
No more basis in saying that than I do. That the universe is free.
I have evidence.
But I have evidence too. That's exactly my point. That, the big philosophical sea change with quantum mechanics is it revealed,
That's only if you accept an incorrect interpretation.
Pure arrogance. And to give another example, I mean, something kind of similar to Laplace, the rise of computers in the 20th century is a very interesting one because, even as the physicists are discovering quantum mechanics, they're also, inventing computers. And computers are deterministic. And in fact, they are the kind of 19th century dream of these sort of mechanical calculating theorem proving devices. And, far more arguably, at a sort of gut philosophical level, the widespread introduction of computers has shaped how we've thought about the world over the last couple decades. It influenced the way that people think about, say, for example, economics and game theory. The fact that, simple models of self-interested, so-called rational agents could be modeled on computers became, the kind of idol which was worshipped in economics. And, I think you'll agree with me that it's a bunch of mathematicians with their heads up their asses. It doesn't.
Right, exactly. And like I say, I repeat, math is not reality.
Exactly.
Math is a mental construction which sometimes is useful in describing what we perceive as reality. But today, and this is the problem with early 21st century physics, you have people whose entire careers are based on mathematical constructions for which there is no empirical evidence and for which they know their theories can't be tested. And they perpetuate these mathematical theories. Maybe great math, ain't physics, even though they call themselves physicists.
Yeah, so I mean, I could say the same thing about a lot of economics. And I'll just, I'll say it's
economics is all, I'll tell you the problem with economics. You know what the problem is? It's based on equilibrium.
Yeah.
Where do you have an equilibrium? Where do you have an economic equilibrium anywhere? It's in constant flux. And all economic theory that I know is based on equilibrium.
Yeah, we're on the same page about that. Yeah, I completely agree.
So that's all bullshit. We know that.
So, I mean, I just, you know, when I was coming of age and, you know, starting to read things in like the early 2000s, you know, like my friend who I'd argue with, you know, he was really into like the new atheists, Richard Dawkins, et cetera, et cetera. And, you know, the feeling that I was getting from academia at the time, like the kind of intellectual current, was that the metaphor of the computer was like the metaphor, right? Maybe the universe is a computer. Definitely you're a computer. People are robots. And it just seems to me that that in itself is a kind of confusing of a tool and for reality and a kind of promotion of like a certain way of thinking about things to metaphysics. And
At the same time that that view is appearing, though, Matt, at the same time that that view is appearing, which is, you know, simple-minded and reductive and unable to describe, you know, the nature of the intricate, the exponentially intricate inputs that go into the human being and go into the arisal of consciousness, whatever, from the physical realm. It's like it simply cannot describe it. So at the same time that that idea is gaining hold, science is moving into the realm of the sciences of complexity. So let's relate sciences of complexity and of chaos. So let's relate that to the quantum realm. And let's say that in our descriptions that we have so far of whatever you want to call it, even a probability cloud of the position of an electron as it moves around a hydrogen atom, okay, we have very clear parameters to the shape of that probability cloud. In other words, for all the indeterminacy or indetermined qualities for the point-like particle or for the wave packet or for the oscillation in the quantum field that is being expressed there in that image, it is highly defined. What is more, the quantum mechanics is, based upon the initial versions of quantum mechanics are based upon a probabilistic model, but that probabilistic model leads to a predictive outcome which has a certain precision to it. In fact, it's correct until the contracted version of quantum mechanics dealing with the movement of electrons around atoms and molecules, which is more accurate. It's about 85% accurate. So what we've got is signs of complexity rather than randomness. What we have is absolutely clear signs of complexity, which is ordered. Complexity is ordered. It's and even if it seems like a disorder, it's an ordered disorder or a disordered order. So as soon as you want to rely on randomness as opposed to some system of order, even if you cannot finally determine it, you're not describing the universe as we know it at this point, because we've passed beyond these simple-minded theories like behaviorism or the mind as a cyber entity, and we have moved rather into the irreducibility of consciousness, even though we're mapping it with MRIs. Okay, mapping not consciousness, mapping whatever the firing of neurons, firing of synapses, the movement of signals along axons, etc. That's what we're measuring. We're not measuring consciousness. So it's when you describe pure randomness, you're not describing the universe at every level. And once again, I have to make the point over and over, every single level of the universe, from the quantum realm to Brownian motion to the three-body problem in space to the cosmological level, is probabilistic. You made that point in your essay by saying that, well, I discovered that at every level in the sciences, they were using computer models, probabilistic computer models. And you said to yourself, what's the point?
By the way, I agree with Victor. You know, there are certain problems like the three-body problem or complexity problems, which we say are non-deterministic because we don't have the math to describe them. That's our shortcoming. That's not the universe's shortcoming. The universe knows what the outcome is going to be because we don't have the math to describe it, or any other method doesn't make it probabilistic or non-deterministic.
With Brownian motion, a single grain of pollen is struck by 10 to the 14th molecules of water per second. So it's a purely deterministic process that is indeterminable for us, at least at this point, based upon our prosthesis, the devices we use to measure. We're not anywhere near being able to take the measurements and find where it will move. But where it moves is utterly determined. And that is an intersection point. If you reduce the Brownian motion to a single grain of pollen, that is an intersection point between the quantum realm and the classical realm, because it's a matter of water molecules striking the grain of pollen. Okay,
now, what I would say in support of Victor, and I made this distinction at the beginning of my presentation, there's a difference between probability and a statistical distribution. Statistical distribution just means that we're describing it that way because it's too difficult in a practical sense to measure the positions and momentum of every particle, as in Brownian motion or particles in a gas. Whereas probability means that it's not deterministic. That what came before doesn't cause what comes later deterministically. That's different from a statistical distribution, where at least in theory, you could measure all the momenta and positions. But as a practical matter, it can't be done.
Sure, I agree with that. And I also agree with Victor's point about, you know, the sciences of complexity, you know, and network science really being something crucially important in the 21st century.
But because we can't describe it doesn't mean that it's not deterministic. It's our shortcoming.
Right,
but not nature's shortcoming.
Let him make his point, Mike.
Moving up to a meta level, there's this sort of notion of like, why, suppose there is one deterministic law that governs everything. Why that law? Am I not allowed?
Why
that law? Am I not allowed to ask that question?
Well, who said there's one deterministic law?
Well, you're saying there's multiple deterministic laws, or the laws can change?
As far as we know, there's no indication that, in fact, there's no indication that there is a theory of everything. This assumption that gravity is a quantum theory is a pure supposition. There's no empirical evidence for that.
You're saying that the world's governed by immutable deterministic laws, but we'll never discover them.
Maybe not. Maybe we don't have the mental capacity.
It's indeed possible.
Why do you assume that we're the ultimate intelligence and we have the mental capacity to understand it?
I don't necessarily. You know,
we only strive as closely as we can with our mental construction known as mathematics, which is the only way we know how to describe it. But then to take mathematics and impose it on the universe, which is what's being done now in physics, is very dangerous.
It's more like if it came out that, you know, it was like, okay, guys, we figured out that one law, that would appear random to me, because it would be like, well, why was it that law? And you'd be like, oh, well, it's consistent with experiment. And then I would be like, you know, how is that? I don't know. It would, so
because it explains everything.
If there's one law, it would have a maddening internal complexity, and perhaps an irreducible internal complexity, if there's one law. And one has to hold up this possibility that there is an array of laws that interact in ways that we may not eventually be able to determine, because we may never have not only a theory of everything, but a theory of absolutely everything, because our theory of everything idea is based upon our notion of the four forces, okay? We've just, the X17, which is about 16.8 mega electron volts, it seems to possibly be a new boson that mediates the decay of beryllium-8, as well as certain hydrogen atoms. And so you've got that, you have dark energy. Maybe there's 11 forces. Maybe there's far more. Let's think about the way in which, because I'm saying that there may be far more forces. Think of the way in which these forces, assuming our four are there, and only our four, think of the way in which they express themselves in the unfolding of the universe. If the Big Bang model is correct, there was a period of inflation shortly after the Big Bang. It was a nanosecond, a few nanoseconds, and that's it. And now, as of about 9 billion years ago, dark energy either kicks in or at least begins to override other processes in the unfolding expansion of the universe and accelerates the expansion. So the way in which the laws express themselves based upon the configuration may not be the same. So it's an open-ended universe for our intellect, but for nature, it's not open-ended.
Question.
Just out of curiosity, Matthew, is this more or less where you wanted to go? Is this what you wanted to share with us?
Oh, yeah, I mean, there's different, so like in my essays, there's different things you could pull out, right? I mean, obviously part of what attracts me to quantum physics is it seems to me kind of linguistic or literary in flavor, and that's why I like it. I
have a question.
About and consciousness, and then also about, like the political implications, who gets to decide what's unscientific and what are the politics of that, and the degree to which the way that people think the world works affects, how they think their society should work. But
question, yeah. What's the difference between a single law, as you call it, and a multiplicity of laws? Why isn't a multiplicity of laws just reducible to a single law? It's just different aspects of the same law. I mean, why are we even making that distinction?
Well, I was thinking about it, because, last I was reading the Wolfram stuff, and I was trying to distinguish between, the kind of point of view of John Wheeler, which is this law without law thing. And in a second, I want to read a couple of passages from that essay. From this Wolfram view, where it's something like all the laws that, different observers choose different laws, but you could use any law, like in the same kind of way that, any Turing machine can emulate another Turing machine. The difference between kind of law emerging from no law versus the appearance of a single law deriving from the simultaneous application of all laws. Is there some relationship between those two points of view? So that's sort of why I brought it up.
I think you're also tied into this thinking as a writer, and that, you see these prismatic configurations, you read your passage of the Sirens chapter in Ulysses, or the Anna Livia Pluribel in Finnegan's Wake, and that is where in particular you see the 16 readings that you mentioned where Joyce is writing in Meta-Norwegian, and then, and what you want is to recreate either in the cyber realm or in the realm of theoretical physics the conditions of the writer in a state of invention. You literally used the phrase possible worlds. Okay, so here's I'm going to end there, but I wanted to say that I'm distilling down the schools of thought that have been talked about here. You can call Copenhagen many trajectories, and then you have many worlds, and then Wolfram is many rules. And that is why you find affinities there as a writer who's in a, this keen state of invention.
You're confusing science with fiction, Victor. First of all, many worlds can't be tested, and Everett knew it.
I'm not affirming many worlds. I'm describing the mind of Matt and how it relates to the ideas we're discussing.
But what I'm saying is that science is based on empirical evidence. Richard Feynman said, I don't care how beautiful your theory is mathematically.
To understand the world. And, there's different sources of intuition about that. And that's one of the points I was making in the essay, that, Bohmian mechanics gives you this sort of intuition having to do with trajectories. On the other hand, many worlds is much more adept at giving you intuitions about, for example, how the tensor product should work. Why, for example, in a Stern-Gerlach experiment, there's no interference between the two different beams that might exit, along both paths, because in a way, they're in different quote unquote worlds, each associated with spin being up and the other with spin being down. But of course, even that metaphor has its limits. In other words, the possible worlds aren't really parallel universes, but can rejoin and intersect.
How about this for a very simple explanation of spin up and spin down, and for the fact that the distribution is 50-50. What we call the particle is a wave packet. Spin up is the peak of the wave, spin down is the trough of the wave. End of story, end of your Copenhagen interpretation, end of your many trajectories, your many worlds, and your many rules. All it is a wave packet. And I have seen my only recent image of a recently imaged version of the quantum world. I don't mean the one of that I shared with you. This is of photons, and it was electrons that were used to image the photons. There's nothing particle-like there. It's wave packets, and these wave packets have nothing even mildly resembling a spherical shape, but there are peaks and troughs. And so my spin of my particle, in the case of photons, a massless particle, which makes it very difficult for me to believe firmly in the particle nature of wave particles, because of the fact that we have massless particles, which seem to strike me as even more insubstantial than our mass particles. What I see is peaks and troughs, and so my peaks are my spin up, my troughs are my spin down, and there's my 50-50 distribution. There's a physical description of why we get a 50-50 distribution.
And that image was built up, I'm sure, over many experiments, and it was simply shown. I mean, the sense in which they were visualizing entanglement was to show that the angle.
This is not the entanglement image. This is actually just an image of electrons being used to image photons, and the photons are in a wave pattern that is mildly parabolic looking, but it's narrower than it is, far narrower than it is wide. It is a three-dimensional wave packet, as opposed to these, simplistic two-dimensional graphs of wave patterns. And so it's an image, one of the first images I have seen of the quantum realm that tells me something with clarity about the actual nature of the quantum realm. And what I see is, at best, waves or wave packets or oscillations in a quantum field, and they have a very specific shape.
Yeah, but look,
and they do have peaks and troughs.
The direction in which things impinge on you, and the time at which they impinge on you, can be entangled. And so that's what you're seeing. But, you know, you're not seeing the thing itself. You're seeing the fact that the directions things are coming in at, and
It has an incredibly clear shape. Unlike unlike what looks like a probability cloud in the entanglement image, okay, this has a very clear shape. Now, I don't know to what extent the programmer smoothed things out and made it seem to have a geometric coherence, even though it's the shapes are irregular. It seemed to have a geometric coherence that perhaps is not there, or perhaps not there to that, is not there to that degree, but it really it's one of the first times that I had an image of the idea that I've had about the quantum realm now for almost 40 years.
Victor, that does not explain entanglement. It's a very interesting
I'm not talking about entanglement.
observation.
I'm not talking about entanglement in any way.
You're talking about spin?
I'm talking, well, I did use the idea of spin, and I use this as a confirmation of it. It's not the entanglement image that I posted. It's a separate image. That's more, I think it's more recent.
No,
but it is specifically of photons.
We know
there must be 20 or so.
We know there is no
photons or
such
so.
thing as a point particle, just as there is no such thing as a point. Particles are spread out over space and time.
I agree.
They are field excitations of a quantum field that is spread out over space and time. So of course, they're not point particles as they are sometimes idealized, because in fact, a point doesn't exist in the real universe. What is a point? What is a line? What is
What's
a
the
plane?
point, Michael?
These are mathematical constructions that we use to approximately describe what we see. So of course a particle is spread out over space and time. We know that from quantum field theory.
Diverting a little bit, I wanted to read just a little bit of this Law Without Law essay. I really recommend you guys read it. You know, it's very like beautifully written, and I won't read the part that is perhaps most famous, where he analogizes the participatory universe to a game of 20 questions, where, however, there is no preconceived notion about what word has been chosen. In other words, you know, in the game of 20 questions, you know, you come with the word electron or whatever, and then someone's allowed to ask the questions, and, you know, you have to, you know, blah, blah, blah. But he analogizes the universe to a game where there is no preconceived notion about what it is, but that the answers that nature gives are always consistent with each other, but depend both on the questions that you pose to nature and also nature's ability to, you know, answer. So, you know, I recommend reading that. But
I just want to let you know, Matt, before you read this, I happen to have nature right here sitting next to me. And so if you say something that in any way contradicts her, I'm going to bring her in.
Bring it up.
Okay? Go ahead.
So, you know, he makes an analogy with, you know, like Darwinism, natural selection, right? He says, are the laws of physics eternal and immutable, or are those laws like species mutable and of higgledy-piggledy origin, which he takes from a quote from Darwin. The astronomer Sir John Frederick William Herschel says, my book is The Law of Higgledy-Piggledy. He says, the hierarchical speciation of plant and animal life we now know arises out of the blind accidents of genetic mutation and natural selection. Likewise, the gas laws, the pressure, volume, temperature relation for water and other substances, the laws of thermodynamics take their origin in the chaos of molecular collisions. But as for the molecules themselves, the particles of which they are made, and the fields of force that couple them, is it conceivable that they too derive their action, their structure, and even their existence from multitudinous accidents? Such questions about the plan of physics we would hardly raise if we had the skeleton of it in hand, but we don't. Now and then we meet a colleague in another realm of thought who still thinks physics is in possession of this plan. He cites the word of Laplace.
Can you just speak a little bit more sharp, because I have this terrible hearing problem. I'm sorry.
He cites the words of Laplace and reiterates the Laplacian vision as he understands it. The laws are definite, the initial coordinates, momenta are definite, and therefore the future is definite. The universe is a machine. No, we have to tell him this is a cracked paradigm. Quantum mechanics allows us to know a coordinate or a momentum, but not both. Of the initial value data that Laplace needed, the principle of complementarity or indeterminacy says have, do not, and cannot exist.
Look, Wheeler is a Copenhagenist, and he's married to the idea of point particles. You know, the Heisenberg uncertainty.
I know. Here's the real part I want to read. The only thing harder to understand than a law of statistical origin would be a law that is not of statistical origin. For then there would be no way for it or its progenitor principles to come into being. On the other hand, when we view each of the laws of physics, and no laws are more magnificent in scope or better tested, as at bottom statistical in character, then we are at last able to forego the idea of a law that endures for everlasting to everlasting. Individual events beyond law, events so numerous and so uncoordinated that, flaunting their freedom from formula, they yet fabricate firm form. What Wheeler's trying to do in this essay is think about, in a way, what comes after physics. Like after we've discovered the laws of electrodynamics and, you know, quantum gravity even, the question remains, why this law? Why these laws? Why something rather than nothing? How does the universe itself come into being? And I don't mean the Big Bang. I mean existence itself. And he sees, you know, his way of thinking about it is that the active creation of the universe is happening all around us. That in the act of quantum measurement, whatever that is a kind of elementary act of creation. And that every one of these acts of creation is the same kind of thing that originally gave birth to the universe. And even today, this process of creation continues.
Can I ask a question?
Mm-hmm.
Can you say, well, and this is the time-worn question, how did the universe come into being? But the other question is, can you even imagine nothingness? You know, we have a law called conservation of energy. So the energy has always been here in one form or another. And so the question is to all these people who believe in creation, can you even imagine nothingness? It's not even imaginable.
When I was 5 years old, and then again when I was 7, I was sitting in a class, first in kindergarten and then in second grade. I was sitting in a class, and here was the sequence that went through my mind. I am not. And I was in an absolute darkness.
No.
The space was somewhat confined, but it had depth. And so I had somehow, through thought, you know, annihilated myself. I made myself into an anti-Cartesian at the age of 5, and then again at the age of 7. So I'm not saying that there ever was such a thing as nothing. I don't even believe that. To me, the very idea that space and time were created by a Big Bang is a logical absurdity. Because if you have a quark-sized point, there has to be something outside the quark-sized point. So there may be, and furthermore, nothing will come of nothing. So there has to be a way that there is, even in a confined space, even in a multiverse, there has to be a way that a perturbation can occur that causes a baby universe that, for me, has things gathered within it that it then begins to extend itself into space. So I do not accept the whole notion, this theological notion of space and time somehow being created by the Big Bang. This is theology. This is medieval theology.
Let me tell you what it is that we know for sure about nothingness and what it is that we don't know about nothingness. One thing that we know absolutely for sure about nothingness is that nothingness can spawn a universe like ours. We know it because our universe
No.
exists.
That's not
Don't interrupt
nothingness,
me.
Moshe.
Now,
Let him
don't
finish. Let
interrupt
him
me.
finish, Michael.
Now,
Let him finish.
once nothingness has spawned a universe like ours, there are several possibilities, and we don't know which one it is. One possibility is that that's it. The nothingness has been transmuted into our universe, and the nothingness that was there before does not exist anymore. Another possibility is that after it spawned our universe, it has not been affected, and it continues to spawn other universes like ours, or maybe not like ours, and it will continue to do so for as long as it wants. Another possibility is after it spawned our universe, it changed state. And in its new state, maybe it can spawn other universes, maybe it cannot spawn any other universes. We really don't know. The only thing that we do know about nothingness is that it can and it did spawn our universe.
All right, Moshe.
All we
Moshe,
know
what
about
you're
is that
talking
Sarge
about-
sold a lot of books.
What you're talking about, Moshe, sounds like chaotic inflation. Andre Lin's chaotic inflation. You're confusing what I mean by nothingness. Nothingness is not empty space or some pre-existing state before the universe was created. Nothingness, and the question is, well, why is there something rather than nothing? The question is,
Thank you, Martin Heidegger.
can I finish? You know, Victor, you go on and on and on and on.
I'm not going on. I made a little witty comment. That's it.
Okay, well, tickle me so I'll laugh. The point is, and this is what religionists keep asking, well, how did it all get here? And we have an answer: conservation of energy. In any theory, you're talking about conservation of energy. But here's the thing, and I ask the question to religionists and everybody else: can you even imagine what nothingness is? How
No.
can you? What does that even mean?
No one can do it. No one can do
I
it.
agree that there's an incomprehensibility to it at that level. I mean, I'll say, Wheeler here is not, he like specifically says, when he says nothingness, he's not talking about like the vacuum, for example, or not necessarily something part of like a physical theory, the way that we understand it. But before I say what I'm about to say, I just wanted to ask Victor if he's ever read Samuel Beckett's The Unnameable.
Absolutely.
5-year-old.
I was utterly obsessed with the entire trilogy. I'm sorry, 1 second. I shall soon be quite dead at last in spite of all.
Let me make a suggestion. How about if we stick to questions that can be answered with falsifiable answers? We only stick to those questions where the answers can be falsifiable.
So, okay, well, check out this argument. So this is like another part from this this Wheeler thing. He says this. When we say, because I think what he's trying to do here is change the terms in which the question, why is there something rather than nothing, is framed. In other words, it's like, you're right that there's a certain religious quality to that. You're imagining there's a kind of vast metaphysical nothing, and then, God, let there be light, and then there was something, right? Like the question, in even posing it that way, why is there something rather than nothing? The answer is really can only be something like God did it.
But empty space is not nothing. That's the
Right.
point.
So I think what he's trying to do is like see if there's a kind of both and way of thinking about nothing versus something, and creation, without getting stuck in this like dichotomy of like nothingness and then like, looks fiat, then the world exists. And he, says this: when we say out of nothingness, we do not mean out of the vacuum of physics. The vacuum of physics is loaded with geometrical structure and vacuum fluctuations and virtual pairs of particles. The universe is already in existence when we have such a vacuum. No, when we speak of nothingness, we mean nothingness, neither structure, nor law, nor plan. A conception more clearly impossible I've never heard, says his unnamed interlocutor. Preposterous, we have to agree, is the idea that everything is produced out of nothing. As preposterous, but perhaps also as inescapable as the view that life had its origin in lifeless matter. But how? Leibniz told us, for producing everything out of nothing, one principle is enough. Of all the principles that might meet this requirement of Leibniz, nothing stands out, of Leibniz, nothing stands out more strikingly in this era of the quantum than this, the necessity to draw a line between the observer, participator, and the system under view. Without that demarcation, it would make no sense to do quantum mechanics, no sense to speak of a quantum theory of measurement, no sense to say that, quote, no elementary phenomenon is a phenomenon until it is an observed phenomenon. It's a quote by Bohr. The necessity for that line of separation is the most mysterious feature of the quantum. We take that demarcation as being, if not the central principle, the clue to the central principle in constructing out of nothing everything. And then his interlocutor says this: let me ask if your reasoning couldn't be turned around. You talk of the observer participancy of quantum theory as the mechanism for the universe to come into being. If that is a proper way of speaking, would the converse not also hold? The strange necessity of the quantum, as we see it everywhere in the scheme of physics, comes from the requirement that, via observer participancy, the universe should have a way to come into being. If true, and it is an attractive idea, it should provide someday a means to derive quantum mechanics from the requirement that the universe must have a way to come into being.
Matt, why is he
We've
limiting this to
got this
quantum
whole-
mechanics? Why is he limiting this to quantum mechanics? You could make the same argument for classical physics.
So let's make the argument in the realm of classical physics that leads us into what are essentially medieval theology and metaphysical constructions of something coming from nothing, and it is the relativistic equations. And here is something I've never presented this idea to physicists. I am not a physicist. I didn't have a single class in physics in high school. I had a class called Physics for Poets at a university, and I have done a good bit of reading, and I read Science Daily and physics.org and all of that. So the problem lies in the relativistic equations, not only that give us singularities, but talk about space and time somehow unfolding, beginning with the Big Bang. So what if the mathematics were correct? I'm not questioning the mathematics in spite of the fact that I question the notion of a singularity in a black hole, supermassive black hole at the time of the Big Bang. So there is a mathematical error, but I think in general, the mathematics have shown themselves, shown their precision. So here's my problem. I think that the mathematics, most of the underlying mathematics in the equations of relativity are correct, but the conception is wrong. What is wrong is, and please bear with me before you start attacking, but what is wrong is the notion of space and time being created with the Big Bang, and thus of space contracting and time dilation. And here is a very simple way, which certainly fits in with Occam's razor, the simplest and most elegant explanation of what occurs, for instance, in a black hole collapse. It is not the space that collapses, it is the content of space that collapses. Whether it is photons of all kinds, whether it is neutrinos, whether it is any of the other particles, plasma, that are collapsing at the time of the Big Bang collapse. It is they that collapse, not space. And then when you have the black hole that forms, this is a point I've made, but I haven't made this whole relativistic point to you guys in the New York Quantum Group, that time does not in any way end in the Big Bang, even if there is a singularity, and I doubt that distinctly. And for this reason, that the black hole continues to move through time. We observe it now, 11 years from now, and 111 years from now. So it's what you get is the effect of temporal dilation, and what you get is the effect of spatial contraction, because these are simply human observations of clocks and the way they act based upon their speed, and also the behavior of light, as it bends around a black hole, a neutron star, the center of the galaxy, whatever it is. And so we've got the conception of relativity entirely wrong. The mathematics, short of the issue of the singularities, is correct, but the underlying conception is wrong. And that brings us into the possibility of something before the Big Bang, if there was a Big Bang. And it brings us into the possibility of all of these cosmological models that can be entertained and should be. And it brings us, and it meets Occam's razor.
Matt, are you on tomorrow?
Yeah.
You're gonna be at 1 o'clock?
Uh-huh.
Okay, I gotta go. Thanks for everything. Thank you, Victor,
Thank you
for your enlightening speech.
Yeah, no, you really did a great job with your presentation. I'm glad that you did the whole history of all the experiments and everything. It was very clear, and I appreciate you doing that.
Yeah, and I'll tell you, I love a lot of this is philosophical differences, and I love talking about philosophy, because in the end, you never resolve anything. You just keep going on and on.
But it is.
Like I said, I don't believe that we are the ultimate intelligence that can even conceptualize the ultimate nature of nature. I mean, this really takes some arrogance and egomania to even believe that we can ultimately describe the ultimate nature. But yeah, that's what philosophy is. We go on and on.
Michael, before you go, I just wanted to say this. There is more in heaven and earth that is dreamt of in your philosophy, Michael.
No, it's Horatio, not Michael.
Horatio.
I'm changing my name to Horatio. What do you think? You're the only poet? I'm a poet and I didn't even know it. Thanks everybody. I'll see you guys tomorrow.
Take care.
Well, speaking about relativity, I'll say something, and this is sort of a half form, so I don't necessarily stand by it. But it seems to me that there could be an intimate relationship between relativity and the indeterminism of quantum mechanics, in the sense that, suppose you have two spins. Now,
Suppose you have what? I'm sorry, I have this hearing problem. What?
Suppose you have two spins,
Mm-hmm.
and you want to know, well, what's the relative angle between their rotation axes? You could, measure the one a bunch of times through some Stern-Gerlachs, measure the other one, and so forth. But, when you think about describing the state of a particle, it's always, in the case of the spin, with reference to a choice of XYZ axes. In other words, you assume that there is a way of coordinating your sense of XYZ with that of the particles. And, as early as the 60s, Penrose was interested in the case where, what if you lacked a reference frame for the directions of space.
The what reference frame?
A reference frame.
But what kind of reference frame?
A reference frame for the directions of space.
Okay, okay.
So, you know, this is the motivation for his developing of the theory of spin networks. And his basic thought was that, you know, if you don't, like, can't assume that you have a classical reference frame for X, Y, and Z, then you can only measure one spin relative to another spin. And furthermore, you can only measure the total angular momentum. And not the individual components, the XYZ components of that angular momentum.
That's what happens with a black hole.
Maybe so. So, you know, what he does is he shows how, like, for example, you could have like a network of spins, you know. In his original formulation, it was like a network of trivalent vertices. And so, you know, that's not even right. 3 spins come in, angular momentum is conserved at the vertex. And this spin network is a choice of outcomes to these spin interactions. So in other words, if you had a spin half particle coming in and hitting a spin J particle, what could pop out is either a spin J plus a half or a spin J minus a half particle, each with a certain probability. And so Penrose's aim was to use those probabilities to reconstruct what the angle must have been between the 2 spins. And he does this by, you know, laying out a spin network, which is in a sense a choice about, okay, a spin half comes in and it hits a spin J, and then, oh, spin J plus half comes out. Or maybe you draw a different network and it's spin J minus a half comes out. And so you build up a whole network or whatever. And then the idea is, like, you can calculate, you know, the probability that such a network represents a history. What's the probability of that history happening? And what's interesting is that he shows, like, in the limit, where the networks are large and the spin is large, that if you imagine taking out a big spin J and, you know, having it interact with yet another spin half, modulo some details, if you do that between all the different particles and stuff, they all appear to have angles consistent with each other in 3-dimensional space. In other words, you know, this guy's rotation axis is like this, and the relative angle with someone else's rotation axis is like that, and then they're each consistent with them both having an angle relative to a third, which is not necessarily true a priori. And so in a way, it's a bit of a sleight of hand, right? Instead of specifying the exact states, you know, instead of specifying the exact states of each spin,
Okay.
you specify the history of the interactions between the spins, and you can derive the angles between them in a way emergent from their interaction. Okay. Now, you know, what this makes me think of, though, is like the absolute conception of space allows you to say that, okay, here's a thing pointing in this direction, and then over there, here's a thing pointing in that direction. And those angles will be consistent with each other. Like, oh, and this is, you know, pointed in this direction. Maybe Einstein tells us, like, oh, if we actually parallel transport that spin over here, it'll like end up being pointed in this direction. So we like got to be careful about like the effect of moving spins around is, you know, on like where they're pointed and stuff.
What if instead of entangling during the interaction of the 2 particles, they affect the directionality of the spin without entangling? That one spin affects the directionality of the other spin without entangling. I have no idea if that is possible,
I mean,
but as you did it, I mean, why not have an intermediary state between non-entanglement and entanglement, effect of one spin on the other?
well, I mean, I think that would fall outside like the usual scope of, the spin theory.
That would fall within it?
Sorry?
That would fall within it or outside of it?
Kind of outside of it. I mean, obviously you can have particles that are semi-entangled, but my point is this, like we can distinguish like three things, right? In a absolute conception of space, the angles between different things are perfectly definite, no matter where they are, whatever, because space itself guarantees their consistency. If we move then to like general relativity, yeah, basically the same idea, but you have to be careful about how you compare the directions things are pointed in distant locations. You have to take into account their parallel transport. In quantum physics, it's even sort of deeper. It's that through their entanglement, spins keep track of their own relative directions. And they remember it independently of where they might happen to be located in space or time. So, we move from, absolute space keeps track of relative orientations to, curved space-time keeps track of them, but you have to take into account how they move around, to in the quantum conception, each of the spins is just like in itself has like a relationship to the other spins through its entanglement, and so they keep track of their orientation. But once you start thinking about that way, it's like two spins collide, and what if they had no orientation relative to each other at all? Like, in other words, in our like intuitive picture, like we can't imagine that, right? Because we always imagine things immersed in 3D space, and so even if we don't know what direction they're pointing in, they must be pointed in some direction, right? So when we bring them together, they're like, oh, at this relative angle. But if it's two spins in a relativistic universe where relationships are kept track of by the things themselves, that all things are relational, well, what if the spins don't have a relationship to each other and then somehow they're made to interact? What happens? And it seems to me that the answer can only be if something happens. The thing that happens is random. In other words, it's random because there's no prior relationship between the things that could possibly condition what happens.
Well, that's why I was saying what I was saying. So once again, you're in the realm of randomness. So you've got like this order that arises out of entanglement. It's a form of alignment, an alignment of a whole series of quantum properties, and we're talking about spin here. That is why, I mean, I don't think we have the observational capabilities, but it strikes me that in between utter non-entanglement and entanglement, there might be any number of other intermediate possibilities where two spins could have an effect without entangling. Two spins could have an effect on one another without entangling, and instead of it being in any way random, it's deterministic, and we probably haven't even arrived at an experiment to measure this. It comes to mind immediately as you describe it, and my intuition is it's there.
Yeah, but again,
it's there. It's there, Matt.
I feel like in a way though, you're sort of, at least to my mind, misunderstanding like the spirit of what entanglement is. In other words, entanglement is the keeping track of the relative reference frame between two particles. I think that's the best way of thinking about it. It's like to say that, these two particles are entangled means that every time, if I measure this guy to be in some angle, and because of the entanglement, I will also observe this guy to be at a particular angle. Like for each choice of an angle for this guy, there's a choice of an angle for that guy. In other words, it's the thing which allows things to keep track of how they are relative to each other themselves. In other words, it doesn't make much sense to me to think about, an interaction which doesn't cause entanglement. Like in the sense, like you can imagine two spins in a separable state, and then there's some unitary operator that, changes them both, but leaves them separable.
Okay, but so, all right, so
Like
here's the question then. The question is what is the minimum distance, or what is the maximum distance of an interaction between two particles that will not lead to entanglement? In other words, it's less than, they can only entangle if they're within a micrometer of one another, if they're within a centimeter of another, if they're within an attometer of one another. What is the distance at which entanglement occurs? And therefore, here's my off-the-cuff theory. There might be an intermediary spatial distance between two particles that are nearing one another, whatever, in some way, moving past one another, that instead of non-entanglement or entanglement, what you get is an intermediary state, a degree of effect that does not constitute even an entanglement of any single property of that particle.
But again, I feel like, you're kind of missing like the relativistic point here, which is that, the reason that we have to regard like the two spins as
I'm making it up as I go along. I invent physics as I go along. That's what I do.
No, that's fine. Yeah, I mean, so do I. It's like, I, as an observer, have to regard these two particles as entangled, in the sense that, like, I haven't yet figured out like how I'm gonna measure it, like how my XYZ axes relate to this particle. And what the entanglement says is that, like, once I've chosen a frame of reference for this guy, and then I apply the same frame of reference to that guy, the particles are related in this particular way. And the reason it's like entanglement is more than just, the mathematical structure of it is, if I'd chosen a different reference frame for this guy, and then investigated the other guy with a different reference frame, then I would get this answer. And the entanglement keeps track of how I will view the relationship between those particles that is independent of my choice of reference frame. And so, I generally regard, the message of quantum physics is that, it's a deep mistake to think that the world unfolds in three-dimensional space and is made of things interacting, etc. What we have is a situation where there are different modalities, angular momentum, position, these sorts of things, and that through interaction, phenomena develop relationships between each other. And the entanglement structure, encodes these correlations in a way that doesn't depend on, how they, in a way, them being priorly embedded in some space-time. I mean, honestly, that's, the extent to which one can really play that out is subject to debate. But, I brought up the thing about randomness and relativity just to say, when we talked before, a couple weeks ago about the philosopher's donkey experiment, or fable or whatever, where donkey is both hungry and thirsty, and you give him a pail of water and a pail of oats, and then it has no reason to choose one or the other first, and it can't choose, so it just dies. And, in some ways that's analogous to a quantum particle. It's pointed to the left and you're asking it to choose, are you up or are you down? And it's like,
I being more of a consummate ass would choose oatmeal.
Yeah, exactly. Yeah, a little creativity, just combine the two. So, in that discussion, obviously, in any realistic donkey situation, there's always going to be some reason that the donkey might choose one or the other, even if it's just a stray ion in a synapse or something. And so it raises the question, like, as we raised it then, are there ever actually identical circumstances in nature? Like, is there
Are there identical circumstances in what? I'm sorry.
in nature, are there
In nature.
ever literally identical initial conditions? And at first the answer seems like an obvious no, but it seems to me.
I agree. There's no initial condition because you can keep going, infinitely into the past. So I agree with that.
But what I mean to say is that, well, I mean, and that, then you'd probably have to regard the present as the initial condition determining the past and the future.
But the present is a span of time. Always, there's no such thing as an instant. The present is always a span of time. And so what you're measuring is a temporal condition, an ongoing, even in the instant is an ongoing temporal condition.
So, but my main point was to say something like, I feel like if you really take this like relativity, not just special or even general relativity, but this relativity principle that, things are defined in terms of their relationships. If two things don't have a relationship to some degree, like I'm not, for example, the two spins might have a relationship in their position, but not in their spin. And then there may be
libertarians living in Idaho.
If there's no relationship, then it's not a question of, this initial condition being close to that initial condition. They have literally no relationship. And therefore, when they're made to interact, if something happens, the thing that happens has to be random. In other words, like that's my answer in a way to like, what's like the real life or like physics-y kind of, thing that
Okay, wait a minute. I'm sorry. Maybe because it's late. This is such an important point. And if you could, it was probably simple, but because I have this hearing issue, it's as if I can't even hear my thoughts. In like 20 seconds or 30 seconds, explain how you, got to your, the underlying principle that the randomness was there.
If the world is a network of relationships, and if two things along some dimension don't have a relationship, but are forced to interact, then what can result from that can only be random, since there is no reason that conditions anything about that interaction.
There's every reason that conditions that interaction. There is gravity, there are magnetic fields, there are photons that are striking those particles, there are neutrinos, they're passing through those atoms, if they are atoms as opposed to smaller particles. There's an array of forces.
Right, but that's why I said
that is affecting both particles, whether or not they ever entangle, whether or not they establish a clear relationship. They're both in the same quantum fields, and they are, and there's nothing random about any of the interactions or non-interactions. Nothing.
Well, but that's why I specified along some dimension, right? Obviously, if two particles collide, they must have had a prior relationship in position for them to even be able to find each other. So I'm not saying that two things in the universe can be absolutely radically unrelated. I'm saying that along some dimension, some aspect of them might be unrelated. And you might be like, oh, well, but even so, there must be something in the past that could relate them. And I don't disagree with you, but what I would say is this, that the past can be erased.
No, I'm talking about the present. I'm not talking about the past. I'm saying that even if they don't establish a relationship, even of minimal entanglement, even of a single, quantum property, they are in a relationship because they're in an array of spatio-temporal relationships, and they're in an array of fields, quantum fields, And some of these are very fields that act over immense distances, like gravity and magnetic fields as well, gravitational fields, magnetic fields. And so, and then you've got all of the local fields and the quantum foam and the, you know, the particle and antiparticle pairs are coming into existence. Whether or not they even register a relationship, they're in one.
Victor, what I'm saying is those relationships are entanglement. That's what entanglement is. Entanglement is the thing that keeps track of the relationships between things in the universe. So you can't just be like, oh, what if they're da 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 da. In other words, like what we talk about in quantum mechanics is often, right, I could have, you know, a separable state, right? A state where this spin is up and this spin is down. And then I could have like an entangled state, you know? In this case, the relationship is between the two particles, right? And what entanglement does is allow this relationship to be independent of my choice of reference frame. In other words, if I fix a reference frame by choosing to measure like in this direction, then I know because of the entanglement, then, you know, this will end up in that direction and so forth. Now, all these things that you're talking about, you know, but what about the fields and what about this and da da da? Like at the end of the day, all of those relationships are going to manifest in an entanglement relationship between this thing and the other stuff. And that's what entanglement is.
But there is as far as I understand it, there's a presumption about the distance at which the two particles interact that initiates the entanglement that then can be remain entangled over immense distances.
I mean, even so, my point is a little bit different. Now consider this state here. This is a separable state, right? Like, oh, these are not entangled. And so you'd say, oh, these don't have like a relationship to each other because they're separable, right? They're not entangled. Like entangled means relationship, these are separable. But that would be a mistake. These do have a relationship with each other in that they're related to me. In other words, like this is saying, you know, down in the Z direction relative to me, and this is saying up in the Z direction relative to me. In other words, at some level, if I can deduce that this is the state of the two particles, then like we're already entangled. It's just that like from my perspective, they're separable. Now I'm considering then a third case where it's just like the particles don't have a relationship and they don't have a relationship to me. Should they come together and interact, what happens? And I'm saying like this is even like the more fundamental form of randomness, because when these guys come together relative to me, there's like no reason for they to choose anything at all. And so I feel like that's one way of thinking about it. I mean, to your point about
This strikes me once again as so quintessentially observer-based.
Yeah.
Right? Like the measurement problem, you know, so that we are not really talking about nature. We are talking about my perception of nature and my relationship to a relationship. So it's like, so the particles will be related in an array of ways. At any moment, all particles are related. I agree with that. The entire cosmos is related. Even if there's multiverse, it's all part of the same cosmos. Even if there are spaces that are coexist with other universes, it's all the same universe. So everything is in some kind of underlying relation with everything else.
I'm kind of contesting that. I'm saying that, you know, it's possible that things can be shorn of their relationships, that things can be, you know, radically unrelated along certain dimensions. And then when they
You're
come
just trying to vote through a divorce law. That's what you're trying to do.
Hmm?
You're just trying to vote through a divorce law.
Yeah. No, I mean, I think that, like, here's another way of, you know, thing that's worth thinking about. Again, we talk about the observer, and that gets confusing to people. So here's like an interesting way of thinking about this. So, you know, there's work done, you know, it's funny because this is like the mirror image. I think you're seeing the mirror image.
In addition to having this hearing issue, which just arose 2 days ago, I'm already trying to deal with it. Because it's so bright in this room, I can't read the board.
Yeah.
So anyway, this is good for others, but I'm both blind and
I
deaf.
cannot read it.
Blind and deaf, but surely I'm not dumb,
Now
although
I
some
see-
might contest that.
Now I see reflections of lamps.
Yeah, okay, let's put that over here. Okay,
That's
well,
better.
I'll have to deal with the fact that this is a reverse image. Now, again, I present this thing about if two things are like unrelated when they interact, something random happens, as sort of a thought experiment, because I think, yeah, I mean, is it really possible to conceive of a world where things are radically unrelated, et cetera, et cetera? I mean, it's a sensitive issue. And one way of thinking, you know, starting to get intuition about it is this. So, you know, there's work done on like quantum reference frames, which means like several like different things in different contexts. But like, I quite like this idea, which is that, you know, quantum states are always relative to some other quantum system. And what I like about this is that it like kind of removes some of this question about like the observer, in the sense that it provides you a mathematical framework from choosing any quantum system you want and like pretend that's the observer. So what this formalism is saying is, you know, if you have this upstairs, that's like A's perspective on A. And this is like
A is what on A?
A's perspective on A. So A's.
Oh, okay. I'm sorry about the hearing issue. I'm sorry.
And then, so we have three particles, A, B, and C. A, here's the state of, and this is the state of the three with respect to A. So here's A's perspective of A, and this is A's perspective on B and C. And the rule is that, at least for spins, every spin regards itself as being up. Because
Why not?
you're always up in terms of yourself. You know, it's just like, you know, any sense in which I'm like not pointing up is like a relative statement. Like I am always the zero of my own.
I happen to have I'm not joking, I happen to have a good online friend who's in Antarctica, so tell that to him.
Haha. Yeah. So this is saying that, all right, so from A's perspective, A of course is up. And from A's perspective, B and C are in this entangled state. But, you know, what if we were to take B's perspective? How would we do that? Now, later, like in another talk, I'll talk about like the equation that you can like derive this from, but I'll just like give it more heuristically here. So, well, the first thing we can say is that B sees itself as up, because everyone sees themselves as being up and in a separable state by definition. So B's got to be up. But then we know that from A's perspective, B and C are entangled. So if B is up, then C must be up, and if B is down, then C must be down. Well, we've said that B has got to be up. So therefore, C has got to be up from B's perspective. now here's the fun part, like what about A?
Up and down.
Yeah, exactly. A's got to be in a superposition.
Why is only one particle in superposition and the other has a clear directionality?
Because from A's perspective, like when A is up, B and C are entangled such that they're either both up or both down. When we take B's perspective, by definition, B has to be up. Therefore, since these were entangled, C also has to be up. In other words, because of this entanglement, B and C always have to agree. And so they agree here. But whereas here, it was sort of a question, all right, B and C agree, but it's sort of a 50-50 chance whether A and B and C are pointing in the same direction. If from this perspective, B and C are definitely up, then conversely, it has to be A that's in a superposition, 50-50 up and down.
I think this is, I think we're now in the realm of this. If you haven't read these books, you should read them. Italo Calvino's Cosmic Comics
Yeah.
and T0.
Haha.
Because it's like, it's as if it's as if A is observing B and C here.
Yeah.
And the characters in Cosmic Comics and T0 are particles.
So, one thing that this framework does not allow you to do is solve the so-called measurement problem or whatever, in the sense that, although here it seems like we've converted like an entangled superposition into two separable states, we've merely shunted the uncertainty over to A. And like that's generic. But, what I hope this sort of makes clear is that, whether something is in a superposition, whether something is entangled and so forth, is observer dependent. And, also depends on the fact that the same symmetry group acts on all these states. Like they're all spins. And so
You're not going to tell me that particles can't be entangled without an observer. You're not going to make that claim.
Well, in a way, it's whether they're entangled or not depends on there being a particular observer. Like, for example, if you're working...
No, the perception of whether they're entangled or not depends on an observer, but their entanglement doesn't depend on an observer.
It does. Not only in this sense, but also in the sense
This is like solipsism.
No, in a non-inertial frame, like if you're accelerating, for example, or moving through a curved space-time, the entanglement between particles can change from your perspective. And it's not so much that the entanglement can be created or destroyed, it's that by moving in a non-inertial way, your definition of what space, time, and what is a particle, what is the vacuum of particles, changes. And therefore, what you regard as being entangled changes and is kind of shunted around. In other words, even the Hilbert space that different observers would use to describe their world is observer dependent. There's like not just one.
The particle doesn't give a damn about who observes it, who doesn't observe it.
But it
The
does.
entire cosmos is in a relation, whether there are sentient beings, whether there's no other sentient beings in this galaxy or not.
Look,
Particles everywhere in this galaxy are entangled with or without observers.
but do you see how it has nothing to do with sentience, right? I've taken here the perspective of a spin half particle A, and here I've taken the perspective of the spin half particle B. I didn't need to have a complicated self-reflective biomachine to have an observer. I just did it. If I was B or whatever, seeing the world from B's point of view can be done with any quantum system. There's no need for anything special.
The only thing that a particle can see, and this is, I'm trying to be speaking in terms of physics, not metaphysics, the only thing that a particle can see, and which is actually the basis of perception, the basis of sight, is it can be affected by a photon. The photon can alter the energy of the particle, and it's that responsiveness of particles to photons which forms the basis of, the fact that rhodopsin is there in the initial one-celled life forms, which can bring about phototropism, and then it leads to eyesight, in this quote unquote higher life form. So that is the only way in which I know that you're doing a thought experiment here or whatever, but that is the way in which particles,
I would
they
say,
don't perceive, but they are affected
look,
by other particles.
what I'm saying is you're confusing perception with a frame of reference. In other words, physics is not about perception. It's not about the process of perception. It's not about what different observers would perceive. It's about the different worlds that different observers live in and how they're related to each other. In other words, it has nothing to do with perception. It's that, like, by being different physical systems, arguably speaking, they see different worlds. And these worlds are related by, mathematical perspective transformations. The problem with the word perspective, of course, is that it makes it sound like it's a matter of perception. But it's saying, the world, like the physical, quote unquote, objective world outside of B consists of C being in a separable state pointed up and A being in a superposition. If B was a more complicated being or something, maybe B could actually measure some of this shit and figure out that's actually true. But it has nothing to do with whether B actually is complicated enough to do it. And frankly, if B was complicated enough to do it, you'd probably see something different. In this case over here, if we regard the reference frame or zero of the universe to be A, then A would say, well, that even that language is misleading, right? The world for A is this entangled superposition between B and C. In other words, it's not about what A would perceive or what B would perceive. It's about the world outside them. If they regard themselves, see, even that language is confusing, right? It's like, yeah, I mean, there's
It's the world according to Quark.
Yeah. And it's all of our, I think a lot of the problem with this quantum physics is all these languages like perspective and according to, and from, Joe's whatever point of view. It's like systematically our language confuses perception, with, perspective in a more objective sense. You see what I mean? It's like what we're used to in our minds is that there's this room and that's objectively given, and I can take different perspectives on it. And to take a different perspective is to have a different perception of the room. But I think, that's exactly that conflation of those two ideas is what quantum physics is kind of asking us to avoid, to actually keep separate. That on the one hand, there's this question about, perception and, what you can know, or what you do in fact know, what you do in fact perceive or experience. Physics is more about, in a given circumstance, what is it possible to know? What is the maximal possible information that is accessible from a vantage point, whether you do know it, whether you do experience it, whether you do perceive it?
Well, I just wanted to bring it back into the human frame again and say something. I said this at the end of the last session, but many or most who are here had gone, and I wanted to, the observer problem in the sense of the measurement problem, the observer problem in the sense of the measurement problem in quantum mechanics. The issue is this. I mean, we're in a cosmos in which matter, that is not dark matter, assuming it exists, most of its mass is in the quarks, yet our knowledge of the quarks is exceedingly limited. It's essentially a mathematical model. We have seen quark-gluon plasma after the collision of particles, the collisions with protons and neutrons. So we've seen they're not really free because they're in some relation to the gluons, but it's not the relation that exists within the nucleons. So the basic condition of most of the mass of every atom and everything we see around us is based upon our non-observation of what the genuine nature of the strong interaction is between the quarks and then between the nucleons through the strong force. And so we are almost completely in the dark about the basic nature of baryonic matter for this reason. And so not only is, quantum mechanics an incomplete theory, which is what Dirac said, and Heisenberg.
You're pulling back, like you're kind of giving up here. Like you're pulling back from the main issue, which is that like in classical physics, it's like perspectives are all kind of like passive transformations, right? There's just like this world, and then, there's just these different perspectives on it, but, in the end, they're kind of secondary, right?
I'm talking about measurement. I'm not talking about observation, which you're transforming into an abstraction in which you're making particles into observers, which is what Calvino does in cosmic comics and T0. I'm not talking about that. I'm talking about the measurement outside of the observation issue and relativity and relations between particles, relations between spins, entanglement, all of this. I'm trying to make a point about the measurement problem, which I think is really essential. The basic source of mass in the cosmos is not the Higgs, it is the strong interaction, and we have never actually seen it, observed it, measured it. The only way we've even perceived the quarks, other than mathematically, as three shimmers inside of a nucleon, is through collision with nucleons leading to the creation of quark-gluon plasma. So what I'm saying is I'm relating that non-measurement of the reality of the quantum reality to the issue of the measurement problem when you're dealing with position and momentum. I'm saying that we're in the dark, friends, physicists. I can't call you fellow physicists because I'm not a physicist. We're in the dark.
But I think that, again, it's like we almost always measure things that are proxies for other things. After all, the most common way of measuring the spin is by measuring the position after it goes through a Stern-Gerlach. And the whole reason that works is because the apparatus entangles the position and the spin. And so, even though we can't necessarily look inside, stuff in general, it's like to the extent that through a physical process, those things become entangled with things that we can measure, we can like draw conclusions based on it. It just seems to me that, quantum physics makes us confront the fact that all our measurements are proxies, right? It's like the classical world was a world which was like bright and clear and open to view. And, quantum physics makes us confront the fact that like all of our measurements, are not only like interventions, but are, proxies for things, right? It's like even in the ancient world, the argument between whether, we see because light's coming into our eye versus whether, we're shooting beams of sight out at things. And, it's like that latter thing, like we're shooting beams of sight, seems to me that like that sort of fantasy that by seeing the world, we can see it as it is. It seems that
Okay, so let me make a comment that goes back to like some of our philosophical discussion. If that is the case and you accept that, I wouldn't say all of our measurements are proxies. I would say many of them are proxies or are proxy-like intermediate conditions between a proxy and an observation. If you accept that, then what you're accepting is that what you call randomness over and over is the lack of the tangibility and the lack of precision in the measurement and in the observation. That's what you're calling randomness. And then you have the array of whatever, all the particles in all the fields and how they relate to the entire cosmos, and you know virtually none of it, and you're going to postulate a theory about the nature of the quantum realm through proxies, imprecise observations, imprecise measurements. Shouldn't that lead you into a state of sublime cosmological humility rather than the declaration that things are random? What it should lead you into is a state of sublime cosmological humility.
I
You
agree. I
know
associate exactly
nothing. I know nothing.
the view that the world is indeterministic. Like, again, it seems to me that in the face of all this evidence, to continue to maintain that the world is deterministic is...
There's no evidence that it's not deterministic. It's your lack of evidence that leads you to the notion that it's not deterministic.
No, I mean,
Victor, could I try answering that?
Sure.
So a couple of things. So first, with your point about gluons and quarks, I just kind of bring up the issue of confinement. So with the strong force being a short range force, that's where kind of particle physics comes from, where it's like you can approximate it as like a particle or a point because everything kind of holds itself together. At least that's how I'd explain it. And then with the whole indeterminism and uncertainty, I would say that it doesn't mean that it's totally uncertain. It just means that you can't, understand energy and time or position and momentum, different pairs of things that, there's just a really small, and defined quantity, defined limit where that, uncertainty principle comes in. So that probably doesn't answer the bigger questions, but maybe it just kind of answers some of the smaller things you're talking about.
Right, well, I have no problem even accepting the notion of indeterminacy. I try to widen the concept into indeterminability, so as to take it out of the quantum realm and bring it into the classical realm and end the distinction between the quantum realm and we're not going to be able to finally determine nearly anything, or we never have finally determined nearly anything. Nonetheless, the world is utterly deterministic. It may be beyond our ken, and we may have to use probabilistic models at every level of the cosmos, but it is likely beyond our ken in the sense of we'll never have any absolute certainty about the nature of anything. But that doesn't mean it's not deterministic.
I just don't understand, how do you explain this fact, right? Again, it's just this is the simplest form of quantum indeterminacy or whatever, right? Here's a superposition state, up plus down. And if I send that through a Stern-Gerlach, goes up half the time, it goes down half the time. But if I send it through an X Stern-Gerlach, then...
An X Stern-Gerlach?
Yeah, instead I measure the spin in the X direction instead of the Z.
Oh, okay, I'm sorry.
Then 100% of the time, it is up. In other words, geometrically, I can think about this state as being pointed in the X direction. And the reason that there's randomness is there's a fundamental ambiguity. It's here's the Z direction. Is this pointed more here? Is it pointed more here? No, it's sort of pointed equally in both. And so when you send a particle oriented in the x direction through a Stern-Gerlach, it comes up in the z direction or down z in the direction half the time, because there's a fundamental ambiguity. You're like asking the wrong question. You're asking a dumb question, you're getting a dumb answer. You're asking, hey,
The dumb question is
how are you
treating
pointing?
it like a particle instead of treating it like a wave packet that has, like, this is off the cuff
This has nothing to
theorization.
do with waves. Nothing to do with waves here.
This is just the spin, no position or anything. It's like,
No, I'm relating spin to the wave nature of the so-called particle. I'm saying that the wave packet, which is the only thing that I've ever observed through imaging, is a wave packet rather than a particle. Because the only time you can see a particle is to see a trail of a particle, and you're seeing it from a distance, and so that is why it seems like it's point-like with a clear trajectory. So if you see it up close and personal, and it's a wave packet, the peak of the wave is the up spin, and the trough of the wave is the down spin.
The peak and troughs of the waves have nothing to do with the spin. No relation whatsoever.
You've seen spin?
It has everything to do with uncertainty. That wave is basically the uncertainty, and that's like the limit I was talking about with the uncertainty principle. That's what you can't know. That's like the limit. So you've kind of like, you visualize as much as you can, and then you're at that wave packet.
No, but you're talking about you're using language to describe an abstraction of the wave function, which is not an observation of nature. It's a proxy wave function that relates to the nature of the quantum particle. It is not, it's not the quantum particle. So if we do observe it, and I just observed it very recently, I saw dimensionality to the wave, three-dimensionality, a wave packet, parabolic in structure with a slight irregularity at its summit. I see clear peaks and troughs in the wave, and I see no example of spin in the image, although perhaps if it was a time evolution of this, these wave packets, I would see that. So I have, I'm trying to say that our use of spin, I said this earlier, is an analogy, just as a word is an analogy, a language analogy. It's a mathematical analogy to angular momentum in the classical realm. We don't know that it's angular momentum. We know that it may relate to the mathematics of angular momentum. That is all we know. We do not know what spin is.
Victor,
I'm postulating a possible source for spin that is not the one that you're using, because I find most of physics, I find the immediate need to question every idea in it, because it strikes me as counterintuitive, random, toys for the mind, proxies, unobserved observations. I'm trying to say, if we're going to be in the realm of science, we need observation. I have an observation, it may be my only recent one, of the quantum realm. It's very clear, it's very shapely, very perceptible.
Let me make a recommendation here. Let me make a suggestion here. You may want to see the series of lectures, at least the first two lectures, by Alan Adams. It is available on YouTube. Alan Adams is a professor at MIT. It's free. And what I like especially about his lectures about quantum mechanics, all he does in the first lecture is just to present experiments. It just shares with you all kinds of experiments, facts of life. You may like it, you may don't like it, you may understand it. By the way, if you understand it, big problem, because no one understands them. But they are facts of life. Those are experimental observations. You cannot deny them. after he presented those experimental observations, I think he waits until the end of the second lecture, maybe the third lecture, to start to build a theory that can explain that, or at least that can describe those observations. Not explain them, but describe them.
Did you say, Moshe, did you say Adam, A-D-A-M, and then Adams, A-D-A-M-S?
Yeah, first name is Allen, A-L-L-A-N.
A-N-N-A-N, okay.
Yeah, Allen. Last name is Adams. And by the way, one of the things about this guy, he's a professor at MIT. In my opinion, he should not get one single penny in salary. The reason is that he's having so much fun teaching this course, he doesn't need any more on top of it.
Yeah,
It is obvious that both he and the students are having a great time. And if you watch it, you're going to have a great time too.
awesome. Yeah, thanks for that suggestion.
Yeah, well, it sounds interesting because because what we're talking, let's be humble rather than, okay, I admit that I have reinvented half of physics. I just reinvented relativity for you. You can accept it or you can dismiss it. And I'm trying to just be intuitively arrive at conclusions based upon observations as opposed to abstractions of wave functions that are not specifically related to nature. So I'm like, I am as much in the dark as all of physics is, only I admit it.
But yeah, again, I mean, to speak to Moshe's point, it's like, I think that, it's easy in the year 2020 after, gazillions and gazillions of esoteric, complicated papers have been published. It's very easy to think that these abstractions are just sort of the fantasies of academics with their heads up their asses and stuff like that. But, the people who just—
I'm not saying that.
Sure, Michael's always saying that, but like the people in the 20s, many of them, I mean, sure, maybe, Heisenberg secretly wanted the world to be subjective in some way, all along, but like a lot of these people were incredibly reluctant to take every single step along the path of quantum mechanics. And the abstractions that they developed were, developed on the basis of trying to explain these experiments. I mean, if you look at how Heisenberg came up with his matrices, I mean, he was like literally like putting data from experiments, like just in matrices, you know what I mean? And like demanding certain conditions of it. Like it was deeply, deeply, deeply tied to experiment. And like that part of the story is like often lost after, 100 years of like high level mathematical sophistication where all sorts of people from other different fields have like tried to see 1,000 different interconnections.
Well, this would explain, for instance, the degree of precision in the Schrödinger equation. I mean, if there is, a high number of observations that were then went into the entire analysis of a set of conditions, conditions that repeat and conditions that alter, you would end up with the mathematical basis for some precision. I'm not questioning the accuracy of the mathematical equations in quantum mechanics or relativity. I'm questioning the conceptions, and I'm questioning the leaps into philosophical conclusions from those conceptions. That's what I'm questioning. I'm not questioning the mathematics, and I don't think Michael is either. Michael's a little bit of a, forgive me, he's a little bit of a Popperian. He's a little bit of a logical positivist, and so he is.
Well, I disagree with that. I would say I'm
restrictive.
the role of the logical positivist here. I mean, he's more, old school. I want a picture of what's happening. Like.
But I want a picture.
Well, but be suspicious.
And I think that's the basis of science.
No.
Okay.
Again, it's not about whether pictures matter. It's like is there one picture? Like, always distrust the single picture. Again, to finish what I was going to say about this, whether you measure this spin, it's pointing this direction, whether you measure this in the X direction or the Z direction, in the former case, it's deterministic. And in the second case, it's probabilistic. In other words, your choice of which experiment to subject this to determines whether you get an answer with 100% probability, plus or minus error, or an answer that's 50-50. In other words, it's not just a question of like, is everything deterministic, or, oh, these results are random. The randomness depends on what you choose to measure. Two different pictures. And therefore, even if you can see like a single picture of like, some
Once again, the very act of measurement alters the state to whatever degree, okay, and alters the outcome. So what you're not measuring the behavior of particles in nature. What you're measuring is your active measurement. It's not so.
Yeah.
So we are in a.
That's exactly the point. Every intervention in the world changes it.
Well, that's clear.
And therefore, we can't actually say the world is independently of us. We have no access.
I'm not willing to say that. That's just too. Yeah, that's too.
That's what it is.
That's an idealist position. I'm not prepared to go there.
That's the beauty of it. That's why I love.
I have to go, guys.
See you, Moshe.
See you
Bye,
tomorrow.
Moshe.
Like in the 19th century, all these like idealists and subjectivists and so-called mystics or whatever were laughed at and made fun of and shat all over by the scientists who thought that like they had discovered the ultimate deterministic theory of all things. And, I have to say, I delight in the revenge of nature to reveal those people to be fools. I mean, I do love it.
I don't think nature has done that. And in spite of the fact that nature has not done that, we can have our Xenakis compositions, and we can have our Finnegan's Wake, and we can read the time passage of Virginia Woolf's To the Lighthouse, and we can, delight in everything from Isadora Duncan to Twyla Tharp. We can be as avant-gardist as we want without having randomness in nature. I mean, we can have Beckett. We can have our Beckett and eat it too.
Well, I'll just say this, that, I mean, I mentioned it in my little paper or in my essay or whatever. And it's actually something that like at tomorrow's meeting, we're going to talk about more. But,
About Sir Thomas More?
it's the combination of randomness and entanglement that allows ordinary quantum mechanics to be consistent with relativity theory. And again, I mean, I'm saying I have some personal motivations for, wanting the world to be a certain way. But, and I can also admit that none of the reasons I could possibly give will rule out something like super determinism, and with a simultaneous necessary ignorance of the observers in a super deterministic world. But when we think about like our physical principles and the way that those principles intertwine, it's the fact that these results are random that allows, relativity to be consistent.
They're random and yet they're quantized. They're random and yet even the probability clouds form into specific geometric shapes. And those specific geometric shapes are determined by the energy level of the electrons. It's quantized, it's ordered disorder, there's no randomness. The word random comes in whenever the mind tires and it can no longer see or it's no longer even possible, given our limits as finite beings, to measure momentum and position at the same time. And thus we start talking about randomness in the same, it's a linguistic error, which is that it's built into the structure of every language.
It's, the motivation is different. The motivation is this. It's something like, if the answer weren't random, you'd be able to transfer information faster than the speed of light. In other words, the randomness plays
But you're claiming that the entanglement takes place faster than the speed of light. That not the transfer of information, but that the condition of entanglement takes place faster than the speed of light. And we have, you know, the rim of the cosmos, of the observable universe, expanding faster than the speed of light. And we had faster than the speed of light expansion. So we have examples in physics where this occurs. I haven't seen.
Like an apparent, you know, moving faster than the speed of light. But
what's that?
Things can apparently move faster than the speed of light, but all right.
Space can expand because space is not a force. Space can expand faster than the speed of light.
Oh, it's not that.
It's just, my point is that this is like not a case where we're simply talking about, you know, the accuracy of measurement and so forth. In order to understand why one should accept indeterminism, it's not just the experiments per se. It's the interlocking of several very important physical principles.
Move away from the term indeterminacy and indeterminism and just say indeterminability, because the universe, that is, once again, the universe that is deterministic, otherwise it would make no logic that it's deterministic in the classical realm and is not deterministic at the subatomic realm. If the universe is deterministic, but it is indeterminable, the issue is of bringing the observer in, bringing the human observer in, is that for us, for our senses, for our devices, for all of our physics and all of its incompleteness at the nano level and the cosmological level, we have for us a lack of ability to make the determination. That our lack of ability to make the determination does not change the nature of anything. In fact, our attempts to measure change the nature of things.
It's like when a theory says that in principle, nobody can determine this. And not only that, but if someone could determine it, it would change the experimental results.
Right.
Then I don't see any reason in supposing that it is determined, that they're really.
Okay, but there's nothing random there. If you can make a choice about the direction, right? About the axis, the X direction or the Y direction or the Z direction. As you're moving through, you choose the X direction, and you come up with a certain result from Stern-Gerlach. Okay, you have named the effect. You have described it. So there's nothing random there. On the basis of your action and the basis of your choice, you have created an outcome, and that outcome is, according to you, foreseeable. There's nothing random there. Nothing.
Whoa.
What this is a misuse and abuse of language that derives from the Copenhagen school, which is now trying to shape a metaphysics, a politics. This is subjectivism.
I have to say,
Would you accept the substitution of probabilistic from randomness, or is that still the same argument?
Yeah, that is what Victor is saying, yeah.
I'm saying that the entire universe is probabilistic for us at every scale. I'm saying the opposite. I'm not taking away probability. I'm saying that underlying the probabilities, the indeterminacy, the indeterminability, the indeterminism is determinism. Because you can't have a universe that coheres as well as it does, forming neutron stars, forming black holes according to a certain mass of a star, you know,
eyeball evolved
mass of black holes, if it doesn't work at the quantum level. You're not going to get that. You're not going to get the order that you have at every level if it's not deterministic.
It's like saying, how could the eyeball arise out of, you know, random natural?
No, that's metaphysics. That's metaphysics. I don't deal in metaphysics.
Well, that's just the theory of evolution. I mean, that's, you know, the religion.
The eyeball, I explained it. I explained it through physics. Particles are responsive, I'm not being anthropomorphic, are responsive to photons. Because particles, okay, quantum particles are responsive to photons. That makes the appearance of rhodopsin in one-celled life forms, which is the same rhodopsin that we have in our retina, responsive to light, and makes a phototropism on the part of that one-celled life form possible. So it arises, eyesight arises out of physics. It's an emergent property. You know, chemistry is an emergent property of physics. Biochemistry and life are an emergent property of physics. And what you get is eyesight out of the initial condition that exists at the time of the Big Bang, which is photons and a quark-gluon plasma.
But following the logic of Wheeler, you could say, and the laws of physics, which we can rely on to provide us with quarks and neutron stars, etc., are themselves the result of a great kind of natural selection, a world fundamentally random at its base, giving rise ultimately over incredibly long periods of time to structure, which we call today law because we don't understand.
Yeah, but okay, structure that we have no idea what is occurring within the structure beyond, you know, the event horizon. We have no idea what is occurring within the black holes. I've heard Moshe, brilliant man, PhD in physics. I haven't heard him. I've gone to two of his sessions. And he didn't really allow for dialogue, so I didn't go back. But you immediately allowed for dialogue. So but you know, with 11 mathematical models for what occurs within the black hole, all distinct theoretical models, geometric models, entropic models, and then because it is in the realm of physics and it's mathematics, we should all be in a state of excitation about the nature of these mathematical models. What I'm saying is, you know, just as we don't know what's occurring in the quantum level, and we require probabilistics, and you know, what we require is an incomplete theory, which is an abstraction of a wave function, which is not the wave or the particle. And so we've got the same degree of knowledge about the inside of a black hole, which is to say, no knowledge of what's really occurring in there. And so I then apply, instead of mathematics, logic to these issues. And that's why I say, rather than the exotic physics of extra dimensions or wormholes, rather than the absolute metaphysics of medieval metaphysics of a dimensionless point outside time in which all the mass is gathered, which is impossible. We've got to have a particle, a space of some dimension in which the matter is gathered so that the scalar field of the Higgs can be active and so that the strong interaction can continue. So it has to have a certain size. That's the only thing that's logical to me. I'm not saying I'm right, but it's the only thing that's logical to me. Occam's razor tells me dismiss the idea of a wormhole or of a extra dimensional space. It tells me dismiss the notion of a singularity. And so what I've got is a hyperdense space of a certain size.
But all this is just like, why are you so certain that the line between, you know, what's inside and what's outside, what's observer and observed, that we've inherited or whatever, is
The line between the observer, I'm sorry, but my ear is getting worse. Hold on.
Why it seems as if, like, one of my big problems with the way that you're framing this stuff is it's like, it seems to me that, you know, you're working with these like received ideas about the relationship.
What ideas?
Received ideas.
It's the opposite.
About the relationship between, you know, observer and
I'm questioning every received idea in physics.
again.
I'm questioning whether quantum mechanics is a complete theory, which Schrodinger said it was not, which Dirac said it was not. I'm questioning whether relativity, even if its mathematics are correct outside of the issue of singularities, whether its conception is accurate.
Okay.
I'm questioning all the received ideas.
You're 100 years too late. I guarantee you that in the decades around the time of the discovery of quantum physics and relativity, every fucking scientist who was born in the 19th century spent their entire lives trying to prove that it was wrong. And there's like novels about it. There's a great book called like Night Thoughts of a Classical Physicist, etc. And the theory has survived every attempt to drag us back into the past.
Except there's virtually not a physicist today. There's virtually not a
quantum physics is a whole bunch of received ideas is bullshit. Like, it's, you know, we call it the orthodox position, but that's ridiculous. Historically speaking, quantum mechanics remains the most radical, heterodox theory ever devised by mankind. And, you know, although people will say, oh, you go read the Upanishads, you can go read this, you go read that, and you can find out, oh, you know, some ancient...
I'm not suggesting that we throw the baby out with the bathwater.
It's like,
I'm questioning the conceptions and the philosophical conclusions that are being drawn from the conceptions. I'm not questioning any and every aspect of the mathematics. And so I'm coming at it from the point of view of a logician and a thinker, as opposed to a physicist who works purely in mathematical models. That allows me to question the received ideas that are implicit in it and the conclusions that are drawn from the underlying conception, which is linguistic.
Logic is, you know, a misleading guide in this case, because, you know, I think you'll agree that logic is, you know, constrained itself by physics or whatever. And
it's constrained to what?
Extended.
Constrained to what?
Logic is grounded in the physical world, first of all.
Uh-huh.
And second of all, you know, what logic is always being extended. I mean, whether, you know, we're allowed to use the law of the excluded middle, whether, you know, transfinite sets will be included and so forth, that, you know, logic itself is like an ever evolving thing. And, you know, what I like want to suggest is that nobody, no philosopher, no scientist in all the grand history of humankind ever anticipated quantum mechanics before some of the most reluctant people on the planet were forced into building this theory by force of experiment. In other words, you know, I'm not saying to just, you know, accept what these people tell you without questioning it. Please question everything. But I'm saying, like, you know, this was not a case of...
I mentioned to you at an earlier session...
...positions going in and seeing this and seeing that. I mean...
I mentioned to you in a previous session that the Pyrrhonist skeptics had an idea of probabilistic nature of things, and they also had an idea that was not. It was not either special relativity or general relativity, but of a relativity in the sense of a relational relativity and the relative position of the observer in relationship to the perception of the nature of things. So the Pyrrhonist skeptics, this is, you know, in the period before Christ, already had many of the underpinnings of modern physics in embryo.
It's like...
Can I say one thing? Doesn't totally relate to that, but so like Michael made a point earlier, which I didn't totally understand. He was disputing Wheeler about, oh, why is he saying quantum mechanics? Why isn't he saying anything about classical mechanics? So my understanding is this, is that classical mechanics is a deterministic theory. And when quantum mechanics came along, it, augmented, subsumed classical mechanics. So it took classical in, took all that determinism in, and improved it and made it better because it found these different faults with classical mechanics that didn't describe everything. So now it describes more. Sorry, I just want to say that.
Yeah, that's absolutely right. And like, I think a good way of thinking about it is, the 19th century, nature was seen as a great economist, in the sense that if you were trying to understand how nature would get from here to there, whatever it was, it'd always take the path of so-called least action. It'd always take the least, most frugal, miserly, puritanical route to get from A to B. And you come up with your equations of motion, and you try to find what's the most efficient way of getting from A to B, and then that would be the evolution predicted by classical physics. In Feynman's conception of quantum mechanics, where it's the generalization of that idea is most clear, the idea is that, in fact, the particle kind of just explores all those possible paths, and which one actually happens is random with a certain probability. And that when you look at the way that the different paths interfere with each other, you get in the limit that the most likely path is in fact the classical path. And so, they can both explain the failure of the principle of least action, like an experiment, because sometimes nature takes these like windy paths for seemingly no reason. They can both explain that, but also explain why, in the appropriate limit, many of those weird paths cancel out, and you get, the thing that in the 19th century people expected to find. So yes, like it both explains a greater class of phenomena, why nature sometimes lazily takes a less than optimal path, but also explains why we even saw the world as classical to begin with.
Light with or without you, and with or without the conception of the, something is rotten in Copenhagen school. With or without that conception, you will continue to live from moment to moment a life of unforeseen possibilities, but they are not for a divine being in whom I do not believe, or the ultimate galactic-sized supercomputer or the vast intellect of Laplace, mere possibilities. They are necessities. And you can continue to live in this super deterministic universe, writing your fiction and imagining that it is you who is writing it, not language that is writing it, not the passages from Beckett that you read that are writing it, not the passages from, the Sirens chapter that are writing it. And so you can continue the illusion, because it is a stunning one, and it's deeply satisfying, and I share it, of life as a series of possibilities.
I feel like you misunderstand me. I'm not interested in like that feeling of possibility. Like, in fact, for me, the experience of writing and making art is precisely that. I cease to make decisions. Like when I'm playing piano, like I'm barely thinking about what I'm doing. In fact, what I enjoy about art is precisely the feeling of determinism, of being guided by the words and guided by the music. Again, it seems to me my ultimate reason for, suggesting that it's not good to tell school children that despite all appearances, the world is deterministic, is that I think it constrains and clouds the political imagination. And there's this like meme going around that, the progress of science has been accompanied by a progressive exile of mankind from the center of the universe. You know, earlier people in their superstitious primitiveness regarded themselves as being the center actor in the drama of existence, and all things were related, and they made these foolish mistakes of ascribing, you know, anthropomorphic nature to the trees and the sky.
We're in the, this is ahistorical because there's no relationship. You know, quantum mechanics, right? Arising, it's sort of like, you know, heyday in the 1920s. Okay, many of these physicists are specifically German. Okay, there are Danes, there are others, but many of them are specifically German. And yet, from this condition of randomness and probabilities, okay, arises what politically? The unraveling of the Weimar Republic, the Reichstag fire, the SA, the SS, you know, Kristallnacht, and the death camps. So, you know, there's no relationship between the ideas in the zeitgeist that have some effect upon culture in the realm of physics. It's not an accident that these probabilities are coeval with the 1920s avant-gardes. That is not an accident. But there is only the most accidental relationship between the open-endedness suggested by these possibilities and the political system that arose in the aftermath of quantum mechanics. It's the same issue if you go back to Laplace. I'm keep using Laplace because I was just in a session on Sean Carroll, and that's one of his signposts. You know, at the time of Laplace, you have the point at which the absolute monarchy vanishes. Okay, a new form of state arises. Instead of having, you know, this a court which gathers all the nobles into the court, this hyper centralization of the state, you have the beginning of, you know, a kind of professionalization of the modern state, of the modern bureaucracy. You have all of these variations on the kinds of associations that occur between two human beings, three human beings, you know, trade unions, professional associations, political parties arising, you know, that are vying with one another. So at the same time as Laplace's, it's not Laplace's demon, it's Laplace's vast intellect arises, you have the very opposite in the realm of politics. And so, and that it's the same thing happens in the aftermath of quantum physics. So what you're doing is you're conflating history and the zeitgeist and political outcomes with the nature of the ideas prevailing in physics. They bear almost no relation.
I see what you're saying. So, I mean, I think there's like a lot of interesting stories you can tell about how, in fact, quantum physics may or may not have, you know, influenced politics. So like, and so like, let me make 2 points. Like one is, I mean, there's an interesting story to tell about, you know, part of the problem is that, you know, in like after the war, science and quantum physics was not associated actually with freedom and indeterminacy and stuff. It was associated with that most violent and material thing, the atom bomb. And, you know, the knowledge was like highly guarded and sort of fenced off by the Defense Department, etc. It had like huge political implications. And that started to change like in the 1960s. And indeed, you know, that's when a lot of people were more interested in like discussing the more subjectivist aspects of, you know, quantum physics, insofar as it did seem to, you know, relate to a lot of the ideas that were floating around in the counterculture. There's a great book, How the Hippies Saved Physics.
I can assure you, then as now, having grown up in the 1960s, I can assure you, then as now, there is scarcely an American, perhaps in Europe, where physics, science, and the relationship between science and epistemology and all of philosophy are taken quite seriously, far more so than in the US. I can assure you that then as now, there's virtually not an American who can tell you what quantum physics is, okay, what are its underlying ideas, what are its formulae, what are its philosophical implications. So while a handful of artists may have looked to quantum physics for its open-endedness in their utopian thinking in the 1960s, or in their avant-gardism, because the 60s revived the avant-gardism of the 1920s, there is virtually no relationship between the ideas of quantum physics and the politics of the 1960s.
I can accept that. You know, I mean, I think there's different stories you can tell, but overall, I do completely accept your point. And I'm really not trying to weave a narrative about how, you know, physics overdetermines what happens in society. I'm more interested in the sort of relational notion of like how quantum physics can be deployed in the course of a political argument. Like, in other words, you know, if someone in a political debate stakes out like a deterministic position and says that, you know, man is inherently this way and et cetera, it's going to be determined, you can't change it, you know, boys will be boys, et cetera.
Obviously, these are not ideas that I cotton to.
Sure, but so you can hit back at them and be like, look, you know, quantum physics leaves it open. Maybe the world's deterministic, maybe it's indeterministic, but like I was saying before, no longer are people allowed to take the sort of high ground and from a sort of scientific position dismiss people who believe in freedom and indeterminism as being unscientific. That's just out. You're not allowed to do that anymore. And that's what I find interesting.
If the world, for instance, is indeterministic, why is it that de Tocqueville, okay, while writing, you know, Democracy in America in the first half of the 19th century, was able to foresee that the two world powers in the 20th century would be the US and Russia? If the world is indeterministic, why is it that, for instance, Nate Silver, okay, at 538.com, in one of the elections, was able to name the winners of every single Senate race and come within a very, very narrow margin of error of the outcome of the election? I can tell you this.
You could say the same thing. How is it that quantum physics and intrinsically indeterministic theory can be proved that in like the macroscopic limit to give exactly the same deterministic predictions as classical mechanics? Quantum mechanics in indeterministic theory can just as easily as quantum mechanics explain why you throw up a baseball and it makes a parabola. It's like, just because something's indeterministic does not mean you can't extract predictions from it, and that those predictions can often be predictions of like 100% probability. Second of all, it's like—
What's his name? Mazziotti? You know Mazziotti? I mean, he's the one who came up with the contracted version of the Schrodinger equation. In order to come between 95 and 100%, as opposed to the average before that for quantum mechanics was between 71 and 94% or something like that. It's basically, you know, if you want to find an average or a mean, it would be somewhere in the middle, somewhere in the area of 84, 85% predictability. His theory for, he reduces the number of electrons that he applies the theory to 2, and through this contracted version of the Schrodinger equation, his predictive power is 95 to 100%. So that's quite remarkable. And I don't question the math. I think that we will utterly supersede it at some point, just as not in the sense of superseding every aspect of the paradigm, as in the case of the relationship between Einstein and Newton.
It's just that, whether quantum mechanics will be extended this way, or whether some of these metaphysical questions will be resolved, and whether or not you can tell a grand story about the intertwining of politics and scientific discovery, at the end of the day, it's like we're alive right now having political debates with people. And what I'm interested in is to what extent can people deploy quantum mechanics in a political argument to score points? And it seems to me that a lot of people.
Yeah, but that's your friends who are you, and you've chosen your friends because they went to Brown, or because they are consultants at Penn, or because they are, cyber, they live at the Cyber Genius Bar, and so they know something of the nature of physics and of quantum physics, and so you have a dialogue with them. But I mean, when I said, that only a few percent
quantum physics in the middle of a whatever, I mean, when someone comes down hard on the way the world is, I think that talking about some of these issues is, a way of shaking up, people's certainty in things. I mean, I do think that, the famous example in the Middle Ages of that sort of hierarchical universe that, you got God on top, and then the king, and then, the nobles over the common people, and then the man over the woman and the children. And, there's this desire that humans have to kind of see this continuity between the cosmos and their political system as this one big fractal or whatever. And it seems to me in the 21st century, we're trying to build a politics that's fundamentally grounded in not just freedom, because freedom's libertarianism, freedom is rapacious capitalism, free to pollute the world. Not just freedom, but consensus and a respect for relationships, and a sort of conception that you can't just take reality as given, but have to do the hard work of getting people to agree and recognizing from what perspective everyone is coming from. And it just seems to me that to constantly be going on and on and on about how despite everything you think and the very appearance of your own free will and everything you think is actually an illusion, and really the universe is determined.
Okay, let's talk
from beginning to end. I mean, that to me is a recipe for depression. It's just
okay, but let's talk about the actual nature of politics and the actual nature of the zeitgeist and the worldviews. We're in the post
I've got to leave.
1789.
Sorry. Bye.
Bye. We're in the post 1789 moment. We're in the era that is, after the Renaissance, after the Age of Reason, after the Enlightenment, after 1789, after the rise of modern democracies in the West, that were submitting the entire world to the conditions of empire, of land theft, of slavery, of forced labor systems, etc. Okay, you've got now very few people living in the West, at least, or living in the more westernized portions of the world, who do not believe in free will. Virtually everyone believes in free will. Virtually everyone. So what has happened is the open-endedness of the idea of free will has become the new received idea, so that it becomes nearly impossible, except if you speak with professional philosophers or even some physicists, to even have a debate about the relationship between free will and determinism, since virtually everyone, based upon the political ethos, I happen to be, someone who believes in, I'm a Nordic style, a left-wing Nordic style social democrat and a radical green. I'm not exactly a conservative, okay? And I think that social democracy is an imperfect model, since it only applies to the well-to-do nations. And where did their wealth come from? It came, such a significant portion of it came out of the scramble for Africa. And so it is the want of others that made for the abundance of those living in the global north. So I don't think for that reason social democracy is the be-all and end-all. But nonetheless, I believe in multi-party systems, parliamentary systems, proportionality in the parliamentary system to have as many possible voices, in spite of the fact that I'm not in any way a libertarian, which is a far-right idea. I'm a civil libertarian who actually has to defend against notions of PC, even though I agree with nearly every underlying idea in PC. I do not agree with their cancel culture. So I want open-endedness, multi-party systems, dialogue, coalition governments, and the maximum amount of civil liberty with the maximum amount of social justice. I think this is a very modern and very open-ended vision. Okay, but
you embody a kind of, in a way, a refutation of my point. You're a determinist and you believe all the right stuff. So, that's
it's that my point is there's no relationship between the two. And so what I'm trying to say is I arrived at these conclusions about free will when I began to realize, wait a minute, all of this is a philosophical, there are previous phases of it. I named some of them. You could go back to, not simply Athenian democracy, you could go back to the origins of democracy in West Africa, where you had the palaver. You talk about consensus. The palaver is based upon the idea of consensus rather than majority rule. And so you have to have a consensus among all the members, all the elders. So obviously it's patriarchal, but all of the elders in the village that have to make a decision in concert. So there's this immense degree of cooperation there. So democracy is something that begins very early, long before the Greeks. And it is something which is actually a rarity in history. While everyone in the West is moving towards, has essentially moved towards the idea of accepting the underlying idea of free will, I began to see that this is a philosophical residue from 1789, and that it doesn't really describe the world, nature, physics as we know it. And I can do whatever I want to write. I wrote it's an unfinished novel that Houghton Mifflin wanted to publish way back in the 1980s. And I'm in the process of writing a book of solutions to the water, food, and climate crisis. So, I'm something of a polymath, but I thrive on the notion or on the illusion of creativity. But philosophically, I look at it and I say, no, it's the easiest way to describe it simply is the Nietzschean idea of a philosophy of forces. There's an exponentially intricate array of forces that are at play in every part and parcel of consciousness. And I cannot determine them, and they arise, the strongest force or the strongest array of forces, the strongest constellation wins out against the weaker and the set of weaker constellations. And that's the decision that's made.
So I would say that but I mean, my whole thing is when I hear that, it, and maybe it's something about my generation or something. Like I hear these kind of neoliberal arguments for free markets echoing in my head.
Oh, I'm like, you know, that's
so complicated. No one
anathema to me.
can understand it. So we just need to let the free markets figure out which forces will overpower other forces and figure out how to.
I believe in, you know, universal health care, universal child care, universal prenatal care and early childhood care, universal child care, universal nursery school, free education all the way through, you know, advanced university degrees, free training and retraining of workers and employees in the workforce, a universal basic income. So I'm about as far from a free marketeer as you can imagine.
Yeah, we're on the same side. And I take your point that there's going to be no simple relationship to, yeah, the politics and you know, this philosophy.
One thing I would say, so this is how I kind of think about it. I don't like to put things in buckets, but I kind of have two buckets that I put the world in. One bucket is poetry. One bucket is what I call mathematics. So the mathematics is like kind of the stuff you learn in physics, you learn in math, the stuff you can draw points between, and the more advanced stuff where we're learning quantum mechanics and different things like that. And then poetry, where I would put politics mostly in like the poetry bucket, where so much of it depends on ambiguity. And reading your essay, I know you talked about ambiguity, and I thought, so one thing where I kind of came to ambiguity was when the scientific method was developed, at least, I forgot the guy's name, but Francis Bacon is like one example that they give his essay. And he kind of broke like, you know, different errors that people make. And one of the errors that he brought up was like the marketplace of ideas or whatever. And what I kind of took that to be, I know you guys talk about language a lot, is word ambiguity. So when we're talking to each other, you know, whether it's English or French or whatever, you know, each word can mean 7 different things. And you guys are really smart about talking about the context and all that kind of thing. But I think poetry and a lot of the human experience kind of falls in that poetry bucket, what I call the poetry bucket. And then, yeah, what I call the math bucket is a lot of the stuff like how would you develop a nuclear bomb, or how would you, you know, do this really cool science stuff, like, you know, like the actual like understanding of how to do it, and the principles and the science and stuff. I throw that in the math bucket. So that's how I think about it.
Yeah, definitely.
And see, what I'm trying to do is poeticize the physics, because I'm, yeah, as he tosses out an idea, I mean, I just invented a possible principle of physics which I don't think we've measured yet. Is there an intermediate state or an array of intermediate states between non-entanglement and entanglement? In other words, without, you know, this clarity of spin up and spin down, for instance, or the alignment of other quantum properties, is there possible degrees of interaction between particles that leads to effects, specifically in the case of spin, but that you cannot name as a clear entanglement in terms of the relation between 2 ups or 2 downs, or up and down superposition, etc.
Well, there's arguments about like why the tensor product is the right idea, and it would be interesting to know, is there something in between concatenation and tensoring? But I mean,
I would bet there is, just because there's so many intermediate states in nature at every level. It just strikes me we don't have the abilities to measure. We haven't even done the experiments. Perhaps someone does. My bet, my intuition is it's there. Go find it and get your Nobel, kiddo, because you should be going to, as I said, Princeton or MIT. That's where you should be going.
Yeah, I mean,
I went to Stanford, not in physics, but I went to Stanford. So go to Stanford because, well, it's just too, I guess it's there's too many string theorists there. Maybe you don't want to go.
Thank you very much. I do appreciate that. I mean,
But I was gonna ask maybe tomorrow. So like you're talking about pure states and mixed states. I mean, you could say, right, that there's degrees of entanglement. That like if you're in the fully entangled state versus, you know, the purely separated state, and then there's the whole in between.
yeah,
Yeah, well, we talked about that. And one property
Yep.
can be entangled, or a number of properties can be entangled. But what I'm talking about is a further intermediate state, which would be an effect. The two spins have an effect on one another, but they're not entangled. They
Yes.
alter their directionality, but not in this clear, you know, alignment condition, but rather in an effect, maybe, for instance, the equivalent of precession, okay, in the sense of the spin of, planets in planetary systems, okay? And maybe there's a precession effect on spin at the particle level.
Well,
Why not?
There definitely is. No, I mean, that's absolutely correct, you know. By the way, have you ever read the book Hamlet's Mill?
Wait a minute, is this the literary critic of, I can't think of his name.
Giorgio de Santayana.
Oh, Santayana, okay. Santayana was,
Oh, not the
one of-
Santayana with the Y. He's like,
Santayana was one of the mentors of Wallace Stevens,
I think that's a different guy. That's like a more early 20th century guy.
the philosopher.
No. Giorgio de, like Santayana with like a L, two L's.
Oh, okay, no, I don't know him, okay.
Science and like literary guy. I think you would like his book. But no, I mean, precession is for real. I think, I mean, Jamie, I think you're right that like in some ways a mixed state is kind of intermediate between, you know, straight up entangled and separable.
Yeah, because I'm thinking of like the Bloch sphere. So like if you're in the center of the Bloch sphere, you're like fully, you know, maximally mixed or whatever.
Yeah,
But then as you go out on the radius, that's kind of like degrees of entanglement. And yeah, I think we might have, I know you've done some of your Python stuff kind of address that. If not, you know, totally directly, you could see it.
Yeah. And to get to your previous point about the buckets of math and poetry, it's like, you know, I think that's like a fair way of dividing things up. And then I guess maybe, you know, what I'm interested in is like, what happens in the midst of a debate when someone takes something from the wrong bucket? You know, when someone in the middle of, you know, a poetry or a politics discussion is like, hey, I'm taking something from the math bucket and like dropping that on the table. Or in the middle of a math discussion, someone starts bringing up some politics or something. When somebody mixes the two, you know, what do you do?
Yeah, no, that's a great point. I just kind of look at the math bucket. For me, it's like a truth bucket as far as like, you know, kind of the falsifiable type of stuff. And then a lot of the errors and stuff and, you know, how we misinterpret things, I put that in the poetry bucket because I think that's what makes us human is the errors and stuff that we make. And even like, you know, on like an evolutionary scale, when you think about like mutations and genetics and all of that, there's these little errors that can happen that kind of like throw everything off from like what you might predict. And, you know, you can predict it, but it just kind of throws a lot of randomness and craziness in there. And those little errors, you know, it's a mathematical error. That's like the mathematical version of the error. And then, yeah, for me, the poetry version of the error is the stuff that we do all the time with, you know, errors of perception and errors of, you know, not getting to the truth. But yeah, again, it's just my philosophy. I just thought I'd bring it up.
I taught literature at two universities, Stanford and the University of the Western Cape. And so I taught poetry, and I was trained in the French school of the explication of the text, which is close reading. And it has some of its origins is in formalism, Czech formalism, Russian formalism, and so forth. So there's a kind of an attempt to make reading into a science. Now, I have no illusion about the possibility of making reading into a science, but what I would say is, yes, every possible reading is there, but at the same time, there are more plausible readings and less plausible readings. So one of the ways in which I sort of apply, I'm making an analogy, it's not the way I work, but I use the principle of entanglement by starting out, for instance, in a reading and circling every word that recurs, or every sound that recurs, or every rhythmic pattern that occurs, and every one where there's similarity, so there's entanglement, but it's not, an absolute entanglement. There's a, and then I start to build out of these simplest levels. I start looking at it from the point of view of physics. I literally analyze the time and space in the poem, and then I start looking at it almost from the point of view of optics, the color palette and the relation between the colors in the color palette of the poem, and it leads to what this one professor of mine in France called, when I did a reading of Mallarmé, he called it the infinite explication of the text. Okay, but one of the things that I did was I took the poem that I read for him in class, and I read it 16 times on 16 separate copies, and I tried in each instance to find an utterly unique reading. But when it was done, I then looked at it phenomenologically and tried to link up the ways in which these 16 so-called distinct readings actually might coalesce into something resembling a unified whole. And in spite of that method, that maddening method between open-ended possibility and formalism, my professor called my reading the infinite explication of the text. So I tried
really... to. Have you? I'm sure
go
you've
ahead.
read Raymond Queneau's Exercises in Style.
Oh yeah.
Maybe think of that.
I wanted to say two things. So yeah, I've been waiting to tell this story because it's kind of on topic, and I don't know, it's a story I've told a few times because it was such a while ago. But first, as far as like the book and everything, what I thought of at first was how John Preskill describes entanglement, and how he describes entanglement is, basically if something was fully entangled, it's like you couldn't read a single page of the book. You could only like understand entanglement by like understanding the whole, like say if all the pages were entangled, like you could only describe that book by properties of the whole book. You couldn't describe it by each individual page or word. But what probably makes up that entanglement is all those connections and stuff. But
wait a minute, Jamie Gill.
Yep.
Do I know you?
I do a lot of meetups. I know I've been pretty loyal.
No.
To
Do
this.
I
Usually
know
I'm
you
off.
through Brian and his wife?
Oh no, so I'm not local. So I'm.
Are you in New Jersey?
No, I'm just taking advantage of the remoteness of things. So I usually hop over on Zoom to Brooklyn and New York on Saturdays and Sundays.
Where are you?
I'm in Wisconsin.
Oh, Wisconsin. Okay.
Yep.
Where they will likely succeed in stealing the election for Trump as they did last time.
We were the tipping point state, I think, last time. Yeah. So.
But if you look at the numbers, I'm a student of this. Trump is going to win the election. In spite of everything you're seeing in the polls, because what counts is a handful of states, and the margins that Biden has now, as Trump is now beginning to close. Obviously, it's going to alter in shape any number of times before the election, so you can't say. What I would say is if we get even the slightest additional movement towards Trump wins the election again, and he wins it illegitimately again because of scrubbing of the voter rolls, because of the voter ID laws, because of the movement of voting machines out of inner city precincts into white, rural, suburban, and Republican precincts. You've got all these people with this sanguine view about what is about to happen in this election, and I think they're in for a dark outcome. On the basis, I've seen the numbers, and they don't work.
What you're saying, dude. I know what you're saying.
Yeah, I mean, I can't speak to those specifics, but yeah, I mean, last time 70,000 votes between Wisconsin, Pennsylvania, and Michigan was the deciding factor as far as electoral, you know, how that goes. I want to tell one quick story to dovetail off of Victor's point about complexity. A while back, kind of halfway through this, I know we're kind of going later than usual, but I'll make it quick. So the discovery of the Higgs boson, supposedly, I guess, according to Michael, but I think it was maybe 2012, around the 4th of July, if memory serves correct. And I live in the Midwest, not too far away from Fermilab. So Fermilab had like a public lecture like the following weekend, or maybe 2 weeks after that in July. So I went down to that. And yeah, so afterwards they kind of had like meet the particle physicists and all that kind of thing. So that was pretty cool. And, you know, kind of got to mix it up with the experts. And there was a philosophy professor, he told me, from the University of Penn. And he was really like kind of challenging the particular particle physics. And I was watching their debate going back and forth, and it's pretty cool. It was just, you know, kind of like this kind of stuff, cool to listen to the dialogue and all that. And so after a while, you know, after listening, I did interject myself, but basically the main objection, and this particular, you know, philosophy professor, he was like a specialist in Aristotle, and he was telling me that Aristotle had like, you know, bad, you know, reputation in science because he was kind of seen as anti-science and that kind of thing. But what he had the problem with was the reductionism in particle physics, that he tried to reduce everything down to points and pick it apart into little pieces. And he was concerned that, okay, these arrogant physicists think that, okay, like you can break everything down into parts and understand everything. And the particular particle physicist like wasn't really able to like refute that very well. So what came to mind for me at the time, I mean, now I probably would mention entanglement, but I thought about, like Victor was saying, with complexity. So I brought up complex adaptive systems. And, you know, I know emergences keep coming up again and again, and the idea of emergence, and, you know, the whole is bigger than the sum of the parts. And so, sorry, it's been kind of waiting to tell that story, but
Yeah, no,
it kind of relates to our topic.
I mean, I think, yeah, I mean, you figure it's like from the 50s onward, you know, like the particle physicists were sort of like, you know, the heroes of the whole field, discovering one particle after another. And, you know, that methodology of like smashing things together at higher energies and looking at what results from it, trying to detect new particles and so forth, is like a paradigm for physics, is like one which, like, you know, I think this, you know, Aristotle professor is not alone in thinking that like that can only take you so far. And that, yeah, like in these days, people are more excited about, you know, what happens when you have, you know, quantum systems that are complicated but ordered, you know, a lot of the advances in condensed matter are kind of like, you know, the result of being able to control, you know, essentially massive quantum states that would have been, you know, not really dreamable, you know, decades ago and stuff. So yeah, I mean, I think, you know, there's a philosophical thing, because it's, you know, it's funny that, yeah, particle physics is totally reductionist, but they're still a little bit holist in the sense that, I mean, they still are working with quantum mechanics, they still work with entanglement, you know, but still they're like interested in what are the basic states, what are the building blocks. And I think that as we get more and more complicated quantum computers and are able to like engineer controllable, massively complicated, multi-partite quantum systems in the lab, then, you know, all sorts of crazy new things, you know, will come out of that. It definitely is. Seems like the
When you think of the quantum realm, and you think of the forces, okay, when you move to the quantum nature of the classical realm, the underlying quantum nature of the classical realm, and when you think about, gravity, I think we will eventually find the graviton if we endure that long as a civilization in the face of the imminent ecocide. But I do think that we will find the graviton. I don't absolutely assume it, but I think that we will. So gravity acts across these long distances. We need a definitive theory of quantum gravity. Magnetism exists, progresses across immense distances, okay, magnetic fields, okay? And then you have the macro implications of the weak force, right? And then you've got the strong force, right, which works only at the smallest scales. But my intuition is that it's intimately linked with gravity. That the strongest force is intimately linked with the weakest force in nature, which is gravity. And the kind of the nature of the interaction is very similar. The attractive nature of the interaction is very similar. So,
But I think the other, I mean, to speak even more to Jamie's point, it's like, quantum field theory for decades was used to predict, what happens in a particle accelerator and stuff. And then I think what you see, like, especially with, these people developing correspondences between ADS-CFT, like this holographic conceptions of black hole, and stuff they can do with condensed matter in the lab, that like there's like a paradigm shift where things like fields, things like space-time are seen as themselves kind of like condensed matter, as being these like complicated quantum systems that are coherent in various ways. And those techniques that the people in condensed matter were developing are now, in the last 10 or 15 years have become like widespread in, like in the foundations of physics and all sorts of other fields. And so, like a sort of reconception of what we even mean by a field, really, as we understand more about, multipartite systems and stuff. I mean, because after all, you can think about, the simplest example of the conformal field theory being, a bunch of spins in a magnet at like a certain temperature. So you have here a condensed matter system, which under certain conditions acts like a field. Once you start playing around with that stuff, who knows how the different forces will be related to each other. And
here's a relating of the macro.
Well, with this, Victor, after you say this, I really actually.
Okay. You mentioned the holographic principle, right? I don't know if you've heard of this theory. I think you're interested with free will. I think you're interested in also the nature of consciousness. So there is actually a holographic theory of memory or holographic theory of consciousness, which is to say that the equivalent of, in a hologram, you shine a yellow light and a blue light and a white light, and a yellow triangle or circle, a blue triangle or circle, and a white triangle or circle. And each time you can actually imprint or draw out of the hologram a completely separate image. So there's a model of memory and of consciousness which is similar, right? You have these, who knows in what way the neurons actually, correspond to one another in their arrays, and how different forms of consciousness arise, but that in the very same space, very limited space, neuronal space, you might have, 111 memories.
Yeah, I mean, I think
have a thousand possibilities for the next phrase that you're about to write in your sci-fi novel. And so,
yeah, I mean, I do think something like that's probably true. I mean, I mentioned in the essay how, like, you can kind of read the tensor product as, allowing for a kind of inwardness. And we talk about, the constellation of a spin J particle being encoded in a bunch of separate spin half particles. It's like, yeah, like in each one of those particles is a kind of image of the whole, but the image of the whole isn't reducible down to what's going on in. Now, how this, again, neuroscience is tough. And I mean, the other day I was talking to somebody who, studies what happens in like synapses and stuff like that. And I was like, do you do quantum stuff? Any cool quantum effects going on, in your ion channels?
Penrose's two microtubules.
And she was like, it's like maybe, but like the thing is, it's too expensive to run the simulations, even if we wanted to run them. Like even today, it's like you got a supercomputer, even that's not enough. So of course they just use classical models. In other words, we're not going to figure out any of this stuff about biology until we have quantum computers, because it's just too expensive to actually run the simulations to take into account the quantum effects. So it's often portrayed like people are like, I mean, there is a bit of like reluctance in the community to like consider quantum stuff, but like I think that's overblown. I mean, the real issue is that, as soon as you put, 17 spins together, becomes like something impossible to run on my laptop. I mean, the dimensionality that you need to simulate quantum systems is impossible to deal with unless you have a quantum computer. So until then, I don't think we're going to be able to answer any of these questions about
Or to simulate consciousness.
brains. Yeah, maybe a quantum artificial intelligence.
I have actually seen.
Maybe.
I don't know if I meant.
I'm not willing to accept a laptop, a classical computer can be conscious. I'm like this much able to accept a quantum computer could be conscious, but I'm not sure.
I have seen this is my last idea, and then I'll shut it off so you can all eat and sleep and live your life and write the whatever the Aeneas, the spoof of Ulysses. Okay, so but I have seen an AI from Japan in a 15-minute dialogue with a human being, and I can tell you this, that outside of some little micro errors in the acoustics of the voice, passed the Turing test for 15 minutes straight.
Nice.
Simplicity, subtlety, erudition, wit, warmth, all of these varied human qualities in 15 minutes, I was stunned. I'm saying that we can already simulate consciousness. We can't simulate any of its underlying complexity, but we can simulate its effect, which is to say, speech.
I recommend looking at some of the stuff that this GPT-3, this artificial intelligence system, has been putting out. It's like a language model, and yeah, maybe I'll post something about it. But look up. Wait, let me post in the chat right now before I forget. It's like
I'm going to share that image of the photons taken with electrons, so you can tell me how you can interpret the nature of the wave particle duality, or the whatever the nature of it happens to be.
Yeah,
on one end of the spectrum.
I'll figure out what exactly are they.
You've got to you have to see this, because I don't want to sound insipid, but it's mind altering to finally actually see an image of what we are theorizing.
Yeah, no, I mean, images are so important. Yeah, I mean, I would never contest that.
Okay, Jamie.
Yeah.
Okay, Matt.
Gotta run. Yeah.
You
Great
run it.
talking to both of you. Until next time or tomorrow.
Great rodeo.
All right, see ya.
See you tomorrow.
Take care.